Welcome to Mechanics of Rest. A generation ship is one of the strangest ideas human beings have ever taken seriously. Not a rocket sent to touch another world, not a capsule carrying a few astronauts for a few months, but a moving civilization built to outlive its builders. The first people aboard would remember Earth as soil, weather, oceans, streets, voices, and gravity. Their children would know it as memory. Their grandchildren might know it as archive. And far later, if the ship still survived, there would be human beings crossing interstellar space who had never seen the planet their ancestors left behind. So how long could such a vessel truly last in deep space? A century, 5 centuries, 1,000 years? The answer depends on air that must keep returning, water that must never be lost, crops that must not fail, machines that must be repaired by people not yet born, and a society strong enough to remember why the journey began. If you enjoy these long journeys through science, history, and the possible futures of humankind, a gentle like and subscribe helps Mechanics of Rest keep making them each week. And while you listen, tell us in the comments where you are listening from and whether there is a person, topic, story, or era you would like us to cover next. Before the ship reaches the stars, it has to become something far more difficult than a spacecraft. It has to become a world. Chapter 1. The Vessel That Must Become a World. A generation ship begins with a demand no ordinary spacecraft has ever carried. It must cross distance, but distance is only the first problem. A probe can sleep through centuries, sealed around instruments and instructions. A crewed mission can survive by taking its supplies from Earth and spending them carefully until return. A generation ship has no such simplicity. It must remain alive while the people inside it grow old, bury their dead, raise children, teach those children the names of systems they did not build, and trust that a machine launched by ancestors can remain merciful to descendants. At first, it may look like an enlarged vessel, a great cylinder or cluster of rotating habitats assembled in orbit, wrapped in shielding, tanks, radiators, farms, workshops, reactors, and guidance systems. But scale alone does not change its nature. A larger spacecraft is still a spacecraft if it depends on stored supplies and scheduled rescue. A generation ship crosses that line when it must produce what it consumes, repair what wears down, and preserve human life long after Earth has become unreachable in any practical sense. Its true cargo is not passengers. Its true cargo is continuity. Gerard K. O'Neill understood part of this problem when he wrote about space settlements in the 20th century. His imagined habitats were not interstellar ships, but they forced a similar mental shift. People could not live indefinitely in space as guests of machinery alone. They would need room, light, agriculture, rotation for gravity, social space, and an environment that did not feel like a temporary emergency. O'Neill's great rotating cylinders belong to the literature of settlement rather than voyage, yet they gave later generations a vocabulary for thinking about enclosed human worlds. A habitat large enough to hold a town begins to ask questions that a capsule never asks. Rotation is one of those questions made visible through motion. If a ship spins, the inner surface can press bodies outward and imitate some portion of gravity. The floor becomes the inside of a wheel. Water falls toward the hull. A child learns to walk in a curve so wide that it feels flat under ordinary feet. Too little rotation leaves bones, muscles, and blood circulation under long biological strain. too much rotation can disturb the inner ear and make ordinary motion difficult. Even the idea of standing becomes an engineering compromise between radius, spin rate, mass, and comfort. Inside such a vessel, the first generation would live among visible reminders that their world had been manufactured. Walls would not be scenery, they would be pressure boundaries. Soil would not be earth in the old planetary sense. It would be managed substrate, compost, microbial life, mineral balance, stored seed, and measured moisture. Air would pass through ducts and membranes before returning to lungs. Water would have a history before every cup. Nothing inside the ship would be merely background, because every background condition would have to be maintained. A planet hides its systems by making them too large to notice. The atmosphere seems to be there. Rivers seem to arrive. Weather seems to happen elsewhere and then pass overhead. A generation ship cannot afford that kind of invisibility. Its climate would have serial numbers. Its seasons might be software schedules. Its harvests would be linked to power budgets, lamp life, pollination plans, nutrient tanks, and the timing of human hunger. The people aboard would not live in nature as their ancestors knew it, but neither would they live outside nature. They would live inside a negotiated copy of its most necessary functions. Project Daedalus, designed in the 1970s by the British Interplanetary Society, showed how serious interstellar thinking often begins with propulsion. That study imagined an uncrewed fusion-powered probe sent toward Barnard's star, with design choices built around speed, fuel, and scientific return. It was not a generation ship, and that difference matters. A probe can arrive silent if it must. It can fail without anyone feeling thirst, loneliness, hunger, or age. A generation ship cannot be judged only by whether its engines can push it between stars. Its engines may stop after acceleration, but its kitchens, filters, nurseries, clinics, schools, and machine shops have to continue. The ship's first century would likely be the easiest to imagine and the hardest to interpret correctly. During that period, the builder's knowledge would still be near. Manuals would be written in living language. Some original engineers might still be remembered by face, voice, or direct teaching. Design assumptions would not yet have become traditions. Spare parts would still match the systems they were meant to serve. If an old procedure seemed strange, someone might still know why it existed. The vessel would be aging, but not yet ancient. A later century changes the problem. The ship would still be physical, still made of panels, bearings, pumps, seals, cables, valves, processors, algae beds, crop rooms, and radiation shielding. But it would also become historical. A repair instruction might be older than the person following it by 200 years. A warning label might preserve a fear no one had personally witnessed. A corridor might carry the name of a dead engineer whose decisions still shaped the pressure behind its wall. In a place like that, history would not sit in archives only. It would be fastened into the ceiling, written into airflow, and hidden in the tolerances of machines. The most difficult part of this inheritance is that failure would rarely arrive as one clean event. A generation ship is more likely to be threatened by accumulation. A crop variety loses resilience. A pump model becomes harder to rebuild. A small microbial imbalance alters a waste processing loop. A group of people begins to ignore a maintenance ritual whose purpose has faded from ordinary memory. A radiation event damages electronics that were already close to their service limit. No single change ends the voyage. The danger lies in changes that become normal before they become dangerous. That is why redundancy would be more than an engineering preference. It would be a moral structure. Critical systems would need backups, and backups to the backups. But hardware alone would not be enough. The knowledge of repair would also need redundancy. No single guild, family, caste, archive, or expert class could safely hold the entire memory of survival. Skills would have to be distributed without becoming diluted. Children would need to learn not only how a filter is replaced, but why the filter matters, what failure looks like, which numbers cannot be ignored, and which old shortcuts were written in blood or near disaster. A world built this way would be crowded with thresholds. There would be places where ordinary living gave way to restricted systems, where a farming deck opened toward a maintenance spine, where a schoolroom stood close to a pressure bulkhead, where a sleeping compartment shared its wall with the slow movement of water reclamation. The ship would have neighborhoods, but each neighborhood would remain tied to machinery. Privacy would exist under the condition of pressure. Community would exist under the condition of circulation. Even silence would depend on fans that did not stop. The outside would remain almost irrelevant to daily life and absolutely decisive to the voyage. Beyond the hull, distance would collect without scenery. Stars would shift too slowly to satisfy human impatience. The destination, if one had been chosen, would remain a calculation for most of the journey rather than a visible place. Yet the outside would press inward through radiation, heat balance, navigation, micrometeoroid risk, and the simple fact that no repair yard waited ahead. Deep space would not need to be dramatic to be severe. It would only need to be unavailable. For the first inhabitants, Earth would remain the comparison behind everything. A tomato grown under lamps might be judged against tomatoes grown in soil under weather. A child's question about oceans could be answered by someone who had heard them. Gravity might still be remembered as something that came from beneath all things, not from rotation. The ship's light-dark cycles might be compared to morning and evening. The earliest culture aboard would therefore live with two worlds in mind, the manufactured one around them and the planetary one that still defined what felt normal. Their descendants would not inherit that balance in the same way. For them, the ship's curve might be ordinary. Its air might be the only air. Its measured daylight might not feel artificial, because artificial implies memory of something else. A garden deck might not be a substitute for a field. It might be the first meaning of green. The vessel would slowly stop being a departure and become an origin. This change would not require anyone to reject Earth. It would occur through birthdays, lessons, repairs, meals, sleep, illness, and all the small repetitions by which a place becomes real. So the answer to how long a generation ship could survive cannot begin with a number. 100 years might be possible for a robust machine with disciplined maintenance and generous stores. Several centuries would require something deeper: ecological balance, social continuity, genetic planning, adaptable industry, and a culture able to revise itself without forgetting its foundations. 1,000 years would make the vessel less like a mission and more like a civilization enclosed inside an artifact. At that scale, survival would mean that the ship had learned to replace its builders with caretakers who no longer thought of themselves as temporary passengers. Before such a vessel ever vanished into interstellar dark, it would have to pass its first test close to home. It would need to leave the planet that supplied every assumption behind its design. It would need to carry the last direct memories of Earth across the point where return became theory, not plan. Only then would the ship's deeper nature begin to appear, as the shoreline of the human world narrowed behind it and the first long work of inheritance began. Chapter 2. Before the last shoreline disappears. Before a generation ship can belong to deep space, it must first pass through the region where Earth still has practical meaning. The planet remains beneath it as mass, gravity, atmosphere, memory, and supply. Every bolt, seed, circuit board, frozen embryo, pressure seal, medical scanner, archive drive, and repair tool has come from a world where oceans move heat, forests trade gases, and weather performs work no machine has to request. Departure begins before the engines commit. It begins when a civilization decides that some fragment of itself must be made portable. Konstantin Tsiolkovsky reached toward that thought long before any machine had escaped Earth. His writings at the turn of the 20th century belong to an age when rocketry still seemed remote from daily engineering. Yet he understood that spaceflight would not remain a matter of fireworks and altitude. He thought in terms of velocity, staging, closed cabins, and the expansion of life beyond the planet that had produced it. His famous work on reactive motion gave space travel a mathematical spine. But behind the mathematics rested a larger idea. Earth was the cradle, not the final enclosure. That sentence has often been repeated because it is simple, though the practical burden hidden inside it is not simple at all. Robert Goddard gave a different kind of answer in 1926, when his liquid-fueled rocket rose from a field in Massachusetts for only a brief flight. The machine did not resemble an interstellar future. It was slight, experimental, and earthbound in scale, lifting for seconds rather than years. Yet the principle mattered because chemical propulsion had moved from thought into hardware. A generation ship would require technologies far beyond Goddard's first launch, but it would still inherit the same basic fact. Leaving Earth is not a wish expressed upward, but a negotiation with mass, fuel, velocity, guidance, and failure. Orbital mechanics makes departure slower and stranger than ordinary imagination prefers. A ship does not merely point itself at the stars and go. It must climb from the surface or be assembled in orbit, escape Earth's gravity well, manage the pull of the moon, move through the wider gravity of the sun, and only then begin to behave like an interstellar craft. Even then, the solar system does not end at the last familiar planet. It thins outward through distant small bodies, dust, magnetic fields, and the long reach of the sun's influence. For many years, perhaps for decades, a departing generation ship would still be leaving home in stages. The first generation aboard would know this better than anyone after them. They would have watched Earth shrink through windows or screens, depending on the ship's design and shielding. They would have carried memories that no archive could fully replace. The weight of natural rain, the disorder of city noise, the smell of open soil after weather, the slight change in air before a storm. Some would have trained for years inside sealed analog habitats and orbital construction yards. But training is not the same as exile. A simulator can end. A voyage like this cannot be paused and returned to its original condition. There would be a phase when Earth remained close enough to answer. Messages might still move back and forth with tolerable delay. Advisors on the planet could help interpret a warning light, a medical anomaly, a software irregularity, a disagreement about procedure. The ship would not yet be alone in the full historical sense. It would be distant, but still held inside conversation. That interval might be brief compared with the journey ahead, yet it would matter because it would teach the crew how dependence weakens before it disappears. A later phase would be marked not by a visible boundary, but by delay. The time between question and answer would grow. Advice from Earth would arrive after decisions had already been made. News would lose its urgency because it would describe a place receding into latency. Births, elections, storms, discoveries, disasters, and celebrations on the planet would reach the ship as messages from an earlier Earth. The crew would still listen. They might still care intensely, but care would no longer be the same as participation. At some point, return would cease to be a real operational category. The ship might still possess the theoretical ability to reverse course, just as a person crossing an ocean in an old age of sail might still turn the vessel around. Yet fuel budgets, velocity, mission design, aging systems, and the biological commitment of the community would make return a different kind of word. It would live in debate, grief, politics, and childhood questions. It would not live in the navigation plan. The last shoreline would not vanish from sight all at once. It would be removed from the list of practical choices. That removal would change the ship's society before deep space changed its physics. The first arguments aboard might not be about destination, but about authority. Earth would still have institutions, sponsors, mission planners, governments, scientific councils, perhaps descendants of those who built the vessel. Did their authority travel with the ship after return became impossible? Did the founding mission bind children who never consented to it? Could a generation born in transit revise a destination chosen before its grandparents were born? These questions are not mechanical, but a generation ship that ignores them becomes mechanically fragile by other means. The law of the vessel would therefore need to begin as more than command structure. A submarine can rely on hierarchy because the mission is finite and return is expected. A spacecraft on a months-long journey can endure strict procedural authority because the outside world remains present as destination or home. A generation ship must govern childhood, inheritance, property, reproduction, education, discipline, research, emergency powers, and descent across lives. If law aboard the ship is too rigid, it may break under conditions the founders failed to imagine. If it is too fluid, it may fail to protect systems whose failure would not forgive improvisation. The first Earth-born adults would carry a special danger in their usefulness. They would know why the ship had been launched, how the first compromises were made, which systems had been rushed, which warnings had been taken seriously, and which had been accepted because no design could be perfect. Their testimony would be precious. It would also fade. A society that depends too much on living memory suffers when memory becomes old, uneven, and then absent. The ship would need to convert experience into durable practice before the last witnesses of Earth became honored voices in recordings. Education would begin under that pressure. Children would learn reading, mathematics, biology, engineering, history, and the practical etiquette of sealed life. But each subject would carry a different weight from its planetary version. A lesson about air would not be abstract. A lesson about microbes would concern food, waste, illness, and oxygen. A lesson about stars would not only explain navigation, because one star behind them had once warmed the world that built the ship. Knowledge would not be ornament. It would be one of the vessel's pressure systems. During this early outward passage, the ship's interior rhythms would still be settling. Crop cycles would be adjusted from design expectations to actual yields. Air recovery systems would reveal small inefficiencies. Water loops would show where contamination liked to gather. Rotational gravity would create practical habits in bodies, tools, and architecture. A drawer closed in one direction, A spilled liquid behaved in another, and a tired worker learned which handrail mattered near a maintenance turn. These details would not feel historic while they were happening. They would become the first customs of the transit world. The destination would also begin changing while remaining fixed in the navigation system. A planet selected from telescopic evidence might look promising across many scientific measures, but no one aboard would truly know what waited there. Atmosphere, gravity, radiation environment, chemistry, climate stability, microbial risk, orbital dynamics, and resource access would remain partly uncertain until much later. For the early crew, that uncertainty might be bearable because Earth still felt real behind them. For their descendants, the same uncertainty could become a different burden. A promised world no living person had chosen, orbiting a star no living person had seen except as data. Deep space, in this early chapter of the voyage, would not yet be the full subject. The subject would be separation. A ship built near Earth must become independent while still remembering dependence. Its people must learn which forms of help can be replaced by stored knowledge, which by local skill, which by redundancy, and which cannot be replaced at all. Every successful adjustment would make the vessel stronger and lonelier at the same time. The process would not announce itself as transformation. It would appear as revised procedures, delayed replies, longer maintenance cycles, and children asking why Earth's answers always came from the past. The last direct view of Earth, whenever it came, would be less important than the last practical reliance on Earth. A camera could preserve the planet's blue-white disk. Archives could keep oceans and deserts and cities in almost endless versions. Songs, languages, maps, laws, recipes, soil samples, seeds, animal genomes, and recorded voices could travel farther than bodies ever had. But the living world itself would not travel. The ship would carry copies, descendants, fragments, and intentions. It would not carry the planetary systems that had made human life easy enough to forget its dependencies. Once that truth settled into the voyage, the generation ship would begin its real test. The question would no longer be whether the engines had placed it on the correct path, or whether Earth could still correct its course from behind. The question would move inward, into every breath and meal, every filter and seed tray, every tank of recovered water, every closed door that held pressure on one side and deep space on the other. A vessel can leave a planet through motion, but it becomes independent only when its own air learns to return. Chapter 3: How Air Learns to Return. Air aboard a generation ship would not be a background condition. It would be an achievement repeated every moment, a living agreement between machinery, chemistry, plants, microbes, sensors, power systems, and human bodies. On Earth, the atmosphere is so large that a single breath disappears into it without consequence. Inside a vessel crossing interstellar space, every breath belongs to a smaller accounting. Oxygen enters the blood, carbon dioxide leaves the lungs, moisture gathers in the cabin, trace gases accumulate in corners of the system, and the ship must keep turning those exchanges back toward habitability before they become danger. The first designers would know that stored oxygen alone could not sustain a civilization for centuries. Tanks can carry reserves. Chemical candles can offer emergency supply. Compressed gases can support short missions or provide margins during failure. None of these becomes a world. A generation ship needs an atmosphere that behaves less like cargo and more like a cycle, recovering what human beings change and returning it in a form the body can accept. The problem is not only making oxygen once. The problem is making the return dependable across thousands of ordinary days. Modern spacecraft already perform part of this work, though at a much smaller scale and for much shorter durations. Carbon dioxide is removed from cabin air before it rises to harmful levels. Humidity is controlled so that water does not collect where electronics, walls, and lungs cannot tolerate it. Filters catch particles. Sensors watch pressure, oxygen concentration, carbon dioxide, volatile compounds, and contaminants that may come from materials or human activity. These systems do not make spaceflight independent from Earth, but they show the first shape of the problem. A sealed habitat begins by treating air as something that can drift away from safety unless it is constantly corrected. A generation ship would need that correction to become almost ecological. Mechanical scrubbers might remove carbon dioxide, but the carbon cannot vanish. It has to go somewhere. Plants can use carbon dioxide during photosynthesis, but plants require light, water, nutrients, controlled temperature, pollination, harvest planning, and protection from disease. Microbes can help process waste into forms useful for agriculture, but microbial communities are not obedient machines. They shift, compete, bloom, decline, and respond to small changes in chemistry. Air returns only when all these exchanges remain inside tolerable boundaries. ESA's Melissa project offers one of the clearest real-world attempts to think in this direction. Its name stands for Microecological Life Support System Alternative, and its purpose is to study regenerative life support through linked compartments that recover resources from waste, carbon dioxide, and minerals. The idea does not treat human waste as an endpoint. It treats it as part of a chain. Microorganisms break material down. Other organisms help transform it. Plants and algae participate in oxygen production and food generation. The full loop is difficult, but the direction matters because a generation ship cannot live by disposal. At the Melissa pilot plant in Barcelona, the work has been approached not as a dream of sealed paradise, but as controlled research into biological compartments. That distinction is important. A closed-loop system is not closed because someone declares it elegant. It has to prove itself through measurements, failures, adjustments, contamination control, and repeatable performance. A bioreactor that works for a period of study still has to be understood under the harsher thought of centuries. Each valve, membrane, culture, nutrient flow, and sensor becomes part of a question that no laboratory on Earth has yet had to answer fully. Inside the ship, the breathing system would likely be layered rather than singular. One layer might rely on chemical and mechanical removal of carbon dioxide. Another might route carbon into biological production. Another would control humidity and reclaim water from breath and transpiration. A further layer would monitor trace gases released by plastics, adhesives, electronics, cleaning agents, cooking, human skin, and plant growth. No single system would be trusted as the only guardian of air. Redundancy would not be decoration. It would be the reason sleep could continue while machines worked unseen. The sound of such a world would be shaped by circulation. Air would move behind panels, through ducts, across filters, past heat exchangers, into plant chambers, and back towards sleeping quarters. The vessel might never be truly silent, because silence in the wrong place could mean flow had stopped. A low vibration in the wall, a shift in fan tone, a change in the faint movement of a vent might become part of ordinary awareness. Children would grow up with that breathing architecture around them, not as machinery separate from life, but as the house sound of existence itself. This is where the ship differs from a sealed room. In a room, stale air is a temporary discomfort before someone opens a window. On the vessel, there is no outside air waiting beyond the wall. The outside is not empty in a scientific sense, but it is useless to lungs. A leak does not invite wind, it spends atmosphere. The hull therefore becomes part of the respiratory system, because keeping air inside is as important as cleaning it. Pressure sensors, hatch seals, compartment doors, emergency masks, and repair kits all belong to the same chain as leaves and algae. For the first generation, air discipline would likely feel procedural. They would train for alarms, know acceptable ranges, memorize emergency stations, and understand the meaning of numbers on environmental displays. A rise in carbon dioxide would not be a vague problem. It would have thresholds, symptoms, and assigned responses. A contaminant would trigger isolation, sampling, filtration, and source tracing. The early crew might still remember Earth air as something given freely by the open world, and that memory could sharpen their respect for the ship's narrower mercy. Their children would inherit the procedures before they inherited the contrast. To them, air quality might be one of the first forms of civic knowledge. They would learn why certain doors stayed closed, why plants were not merely decorative, why a crop chamber mattered to breathing as well as food, why a damaged seal could concern everyone. The lesson would not need to be frightening to be serious. In a closed world, responsibility can be taught through routine. A child who learns not to waste water may also learn not to ignore a vent, because both belong to the same habit of survival. A society aboard the ship might develop manners around air. Strong odors could be considered rude because they burden filtration. Unauthorized chemicals might be treated as communal hazards rather than private choices. Cooking, fabrication, cleaning, painting, medical work, and repair would all have atmospheric consequences. Even celebration would need limits if smoke, vapor, or crowding altered local conditions. Planetary cultures often treat air as public only when it becomes polluted. Ship culture would begin with the knowledge that air is always public. There would also be biological uncertainty. Human beings carry microbes. Plants carry microbes. Waste systems depend on microbes. Some microbial life would be necessary, some harmless, some dangerous under the wrong conditions. In sealed environments, a small imbalance may have more room to matter. A fungus in a growing chamber, a bacterial shift in a bioreactor, or a persistent contaminant in ventilation could move from nuisance to system problem. The ship's doctors and engineers would therefore share a boundary. Health would not stop at skin, and engineering would not stop at metal. The atmosphere would age with the vessel in ways that might be hard to notice at first. Materials release compounds more strongly when new, then differently as they wear. Filters perform well, clog, get replaced, or get regenerated. Biological systems adapt to conditions and may lose diversity. Sensors drift from calibration. A measurement believed to be exact may slowly become less exact unless checked against standards. Across 1 week, these shifts may seem small. Across generations, they become part of the ship's biography. That biography would have to be written in logs no one could afford to neglect. Air incidents, even minor ones, would become records for descendants. A filter failure in year 12 might explain a design change in year 15. A crop room imbalance in year 40 might become a warning in every agricultural manual afterward. A contamination event in year 90 might reshape material rules for the next century. The ship's atmosphere would therefore be maintained not only by fans and leaves, but by institutional memory. Forgetting the cause of an old rule could be as dangerous as losing the tool that enforced it. Deep redundancy would need physical separation. If every air loop passed through one central system, one failure could become universal too quickly. Compartments might be able to seal, recycle locally for a limited time, or isolate contamination before it spread through the vessel. Farming decks, living quarters, workshops, medical areas, and waste processing zones would likely have different atmospheric profiles and different risks. A machine shop does not breathe like a greenhouse. A nursery should not share every vulnerability with a chemical processing bay. The ship survives by being connected, but not too connected. Power would sit beneath all of it. Air circulation needs energy. Carbon dioxide removal needs energy. Lights for photosynthesis need energy. Pumps, valves, heaters, chillers, sensors, processors, and alarms all depend on a reliable electrical foundation. A generation ship with weakened power would not only lose convenience, it would begin losing environmental control. The atmosphere would become an index of the ship's deeper health. When power is abundant, air can be corrected with margin. When power is scarce, every correction competes with food, heat, communication, and repair. The speculative edge of the problem appears when the ship has been gone for so long that none of its original assumptions can remain untouched. Perhaps plant varieties have been selected for reliability under shipboard light. Perhaps algae strains have been guarded like heirlooms because they stabilize oxygen production. Perhaps children learn the names of bioreactor compartments before they learn the names of old Earth rivers. Perhaps certain families or professions become associated with atmospheric stewardship, not as nobility, but as inherited duty. In a civilization this small, a person who keeps air returning holds a kind of power that must be watched carefully. Still, the ship cannot let air become sacred mystery. If the breathing system is too revered, people may fear changing it when change is needed. If it is treated as ordinary plumbing, they may ignore its delicacy. The culture has to find a middle path. Respect without superstition, technical knowledge without arrogance, routine without forgetfulness. That balance may be one of the hardest forms of maturity aboard the vessel. A world that knows it is artificial must never become careless about the artifice. So the ship's atmosphere is not a solved background before the voyage begins. It is one of the voyage's continuing acts. Every generation receives air from the previous one in more than a biological sense. They inherit maintained ducts, calibrated sensors, living cultures, stored replacement parts, written procedures, remembered failures, and habits of attention. Breathing becomes a quiet vote of confidence in all the people who kept the loop intact before the current breath was taken. Only after air can return does the next dependency fully reveal itself. Oxygen may fill the lungs, but bodies also need calories, minerals, proteins, fats, vitamins, and the subtle stability of a food system that does not collapse after one blight, one broken lamp array, or one mistaken calculation. A generation ship must breathe, but it must also feed the children who will one day become its caretakers. And that means the closed world has to learn how to grow. Chapter 4: The Hunger of a Closed Garden. Food is where the dream of a generation ship becomes most vulnerable to ordinary biology. A vessel may cross interstellar distance with engines silent and hull intact, But hunger does not care about distance in the same way. It returns on schedule. It enters the body every day, asks for carbohydrates, proteins, fats, minerals, vitamins, water, and the smaller compounds that keep human chemistry from slowly narrowing into illness. A generation ship cannot feed its people with romance, and it cannot feed them for centuries with stored rations alone. At some point, the ship must grow what it needs, and the growing must become as dependable as breathing. A farm inside such a vessel would not be a peaceful imitation of countryside. It would be a controlled argument among light, temperature, humidity, nutrient flow, microbial balance, pollination, plant genetics, labor, power, and time. Every leaf would occupy volume that had to be built, shielded, warmed, cooled, lit, cleaned, and defended from contamination. Every harvest would represent energy converted into edible tissue under conditions too narrow for carelessness. The ship's agriculture would have beauty, perhaps, but its beauty would be inseparable from accounting. A row of green plants would also be a row of calories, still not guaranteed. Biosphere 2 remains one of the most useful warnings from Earth. Between 1991 and 1993, 8 people lived inside the sealed ecological system in Arizona, surrounded by artificial biomes, cultivated areas, and a structure meant to test whether a contained environment could support human life. It was not a spacecraft, and it was not built to cross generations, but it revealed how quickly confident designs meet biological complexity. Oxygen levels fell. Food production became difficult. Carbon dioxide moved through unexpected pathways. Some species thrived, others declined, and the human community inside had to live with the difference between an elegant plan and a working ecosystem. The lesson is not that closed habitats are impossible. That would be too simple, and it would ignore what the experiment taught. Biosphere 2 showed that sealed ecology is not a machine with leaves attached. It is a living arrangement with feedbacks that can hide themselves until the people inside depend on them. Soil microbes, concrete, plant growth, human metabolism, insects, fungi, and atmosphere all participated in the enclosure's chemistry. A generation ship would have to absorb that lesson with more discipline than any earthly experiment, because it would not have the comfort of opening the system when the numbers moved the wrong way. On the ship, agriculture would likely begin as a layered design rather than a single garden. Some food might come from fast-growing crops under carefully tuned light. Some might come from algae, fungi, or microbial protein systems. Some could come from stored seeds, tissue cultures, or preserved genetic libraries kept against crop failure. There might be dwarf grains, leafy vegetables, legumes, tubers, fruiting plants, and engineered varieties selected for compact growth and reliable nutrition. The exact menu would depend on energy, volume, labor, culture, and risk. Food variety would not be only pleasure, it would be resilience. The surface of that closed garden would have its own practical texture. Leaves would collect moisture differently under moving ship air than under an open sky. Roots would search through substrate that had been mixed, sterilized, inoculated, reused, and measured. Pollination might be done by insects, by hand, by vibration, or by plant varieties chosen to need less help. A seed tray would not be a simple beginning. It would be a small archive of genetic intention. Under lamp banks, growth would have a rhythm, but that rhythm would be purchased through power, maintenance, and constant correction. Calories would impose one of the hard limits. A person can tolerate monotony more easily than starvation, but a population cannot thrive indefinitely on a diet that misses essential nutrients. Crops must be chosen not only for yield, but for amino acids, vitamins, minerals, storage behavior, disease resistance, and cultural acceptability. A plant that grows efficiently but is hated by half the community may create a social problem as real as a nutritional one. Food aboard a generation ship would therefore sit at the meeting point of biology and morale. The meal tray would carry both chemistry and memory. For the first generation, meals might still be compared to Earth. Someone would remember fresh fruit that arrived from another continent, bread made from open field grain, fish from oceans, milk from animals, spices gathered through long trade networks, and food waste that disappeared into municipal systems. On the ship, each of those memories would be narrowed by reality. Large animals would be difficult to justify because they convert plant calories into meat at a cost the ship may not afford. Fish tanks might exist, but they would need water quality, feed, disease control, and space. Spices might survive as treasured crops because flavor can protect morale with very little mass. The second and third generations would inherit cuisine differently. They might not think of ship food as diminished if no other food had ever been ordinary. A festival dish could come from a crop chamber rather than a field, and still become tradition. A child might associate sweetness with a carefully rationed fruit harvest, or comfort with a protein paste seasoned according to a grandmother's method. Culture has a way of making necessity meaningful after enough repetitions. Yet the agricultural system beneath those meanings would remain unforgiving. Tradition cannot compensate for a failed nutrient loop. Pests would travel in strange forms. A closed ship might begin with strict sterilization, but perfect exclusion is unlikely across centuries of human life. Plant cultivation, microbial work, and material movement. Fungi, bacteria, mites, aphids, nematodes, or other small organisms could appear through hidden reservoirs or evolve from managed communities into problems under changed conditions. The difficulty is that a closed ecosystem cannot respond with unlimited chemical intervention. Pesticides may harm crops, microbes, insects, crew health, or recycling systems. Biological control might help, but introducing one organism to manage another can create its own inheritance. Disease among crops would therefore be a strategic threat. A blight that reduces one harvest may be manageable. A disease that affects a staple crop across all growing decks could become a crisis. The ship would need seed banks, genetic diversity, isolated growing compartments, quarantine rules, and the ability to restart a crop line from clean material. Agricultural redundancy would have to be physical as well as biological. If every deck grows the same variety under the same conditions, efficiency may rise, but one vulnerability can travel everywhere. Light would become one of agriculture's central currencies. Plants need photons, and photons aboard a ship must be supplied by energy systems that also support air circulation, water recovery, heating, cooling, computation, fabrication, medicine, communication, and perhaps propulsion-related functions. A farm under lamps is therefore connected to the reactor, the radiators, the wiring, and the maintenance schedule. If power becomes scarce, food does not merely become less convenient. Growth rates change, yields drop, and the community begins spending tomorrow's biological security to solve today's energy shortage. There is another hunger inside the closed garden, the hunger of the soil, or whatever replaces soil. Plants remove nutrients. Microbes transform them. Human beings eat the plants and return waste in altered forms. Minerals must be recovered, purified, balanced, and put back without allowing toxins to accumulate. On Earth, vast geological and ecological systems buffer many mistakes. In the ship, a trace imbalance can become a long-term pattern if no one notices. A shortage of one micronutrient may appear first as weak leaves, then poor harvests, then human deficiency, then a medical record that points backward toward the farm. Biosphere 2's food difficulties showed how human bodies respond when a closed system produces less than expected. The people inside experienced a low-calorie diet for much of the first closure, and the agricultural workload became part of their daily survival. A generation ship would need to avoid turning every citizen into a desperate farmer, yet it could not separate citizens from the food system so completely that they forget its fragility. Automation could plant, monitor, harvest, and process, but automation also becomes one more class of machinery that ages. The farm cannot depend only on hands, and it cannot depend only on machines. Governance enters the garden through rationing before anyone wants to call it politics. Who decides which crops receive space? Who receives scarce foods during medical need, pregnancy, childhood, old age, or heavy labor? How much variety is protected when efficiency argues for uniformity? Whether cultural foods are maintained even if they cost more energy? How famine rules are written before famine arrives? These questions sound domestic, but in a sealed civilization, they become constitutional. Food is never just private appetite when the garden has walls. The speculative future of the ship may include crops that slowly become native to transit. Over generations, plant varieties might be selected for low waste, compact roots, reliable pollination, tolerance of shipboard microbes, predictable nutrient uptake, and compatibility with recycling loops. People may keep old Earth seed lines in protected vaults while also cultivating ship-adapted descendants that would seem strange to the botanists who launched the vessel. A tomato might grow smaller but more reliably. A grain might be chosen less for romance than for protein balance and storage stability. The garden would not preserve Earth unchanged. It would negotiate with the vessel. That negotiation could alter human identity as well. People who grow up in a closed garden may think of food less as a commodity and more as a relationship with systems. Waste from the body returns to processing. Processing returns nutrients. Nutrients return to leaves. Leaves return to meals. Meals return to labor, childhood, pregnancy, repair, study, and sleep. The loop is not sentimental. It is material. Still, repeated long enough, it may teach a culture that nothing eaten truly leaves the world. The greatest danger may come from success that becomes invisible. If the garden works for one generation, then another, then another, its difficulty may disappear from public imagination. Children may complain about meals without understanding the chain beneath them. Leaders may cut agricultural redundancy to gain space for other needs. Engineers may delay lamp replacement because the last harvest was strong. A community can become careless not when a system fails often, but when it has worked long enough to seem natural. On a generation ship, seeming natural is one of the most dangerous compliments a system can receive. So the closed garden has to remain both ordinary and honored. People must eat without ceremony every time, because life cannot turn each meal into a ritual of fear. Yet the culture must remember that each meal is evidence of many systems still aligned. Somewhere, water has moved. Waste has been processed. Light has been paid for. Seeds have germinated. Microbes have done their unseen work. Sensors have kept their watch. Hands and machines have corrected what drifted. Hunger returns every day, and the ship answers only if the garden keeps its bargain. After air and food, the next dependency is even more intimate, because it moves through every body before returning to the ship. Water is drunk, exhaled, sweated, washed with, cooked into meals, taken up by roots, condensed from walls, pulled from waste, and counted again. A generation ship may carry tanks at launch, but tanks alone cannot carry centuries. The vessel's survival depends on whether water can keep finding its way back through the loops that life keeps disturbing. Chapter 5: Water, Waste, and the Discipline of Loops. Water would be one of the first truths a generation ship could not soften. It would move through every person, every crop, every cleaning cycle, every medical room, every food processor, every cooling system, and every hidden place where life leaves residue behind. On Earth, water seems to depart because rivers carry it away, drains accept it, rain returns it, and the scale of the planet makes loss feel ordinary. Inside a ship, departure is only delay. Water that leaves the body must be found again. Water that washes a surface must be recovered. Water that rises as vapor must be condensed before it becomes damage, mold, or waste. A vessel launched for centuries might carry large reserves, but reserves alone do not answer the deeper question. Storage gives margin. It does not create permanence. Even a vast tank can be emptied by enough years, enough leaks, enough contamination, or enough small mistakes hidden inside normal use. The ship, therefore, has to treat water as a circulating inheritance rather than a supply. Every generation would drink what previous generations had already used, cleaned, processed, and returned. That may sound strange only because planets hide the same truth inside clouds. Rivers, aquifers, ice, soil, and sea. Modern spacecraft already recover water because lifting mass from Earth is costly. On the International Space Station, humidity from cabin air and water from urine can be processed back toward usable supply. The system is not romantic, but it is one of the most important practical steps toward long-duration habitation. It teaches that survival in space depends less on carrying purity than on recovering it. A generation ship would need that principle expanded beyond a mission of months or years, until recovery became an ordinary fact of civilization. The first layer of the loop would be human use. Drinking water enters the body, supports blood chemistry, carries heat, aids digestion, moves waste, and leaves through urine, breath, sweat, and feces. Some returns quickly into collection systems. Some enters air as vapor. Some is absorbed into clothing, bedding, filters, plant matter, food waste, or medical materials. The loop has to follow all of it as far as possible. A small loss repeated daily across a population becomes a large loss when multiplied by decades. Humidity would become a kind of hidden river. Every exhalation adds moisture to the air. Every body at rest releases water. Plants transpire through leaves, turning liquid pulled from roots into vapor that joins the atmosphere. Cooking, washing, cleaning, and medical work add their own contributions. If the ship fails to recover this vapor, it loses water and invites corrosion, microbial growth, and discomfort. Condensers, air handlers, surfaces, Ducts and collection channels become part of the ship's watershed, not unlike the slopes and valleys of a planet, except made from panels and temperature gradients. The movement would have a tactile rhythm. Water would gather on cold surfaces only where the system allowed it. Pumps would pull it through narrow lines. Membranes would separate useful molecules from concentrated waste. Tanks would receive, hold, and release according to schedules written by need rather than weather. A filter cartridge would darken. A sensor would drift slightly from calibration. Somewhere behind a wall, a valve would open for a few seconds and close again, and the ship's small inland sea would continue through pipes no child could see. Urine processing would demand a culture capable of honesty about the body. On Earth, many societies place waste outside polite attention, even while entire cities depend on sanitation to survive. A ship could not afford that distance. Urine contains water, salts, nitrogen compounds, and other materials that matter to the loop. Fecal waste carries water, carbon, nutrients, pathogens, and risk. The practical question is not whether waste is unpleasant. The practical question is how much of its value can be recovered without allowing its hazards to spread. That recovery would likely combine mechanical, chemical, and biological systems. Distillation, filtration, oxidation, microbial processing, nutrient separation, and careful sterilization could all play roles, depending on the design. The ship would need to separate water clean enough for drinking from water suitable for crops, water useful for industrial cooling, water awaiting treatment, and water too contaminated to release without further work. Purity would not be one category. It would be a ladder of uses, with each level watched because an error in classification could move danger into a place designed for trust. Agriculture complicates the loop because plants are not only consumers. They drink, store, transpire, and chemically alter water through growth. Irrigation water becomes root moisture, leaf moisture, fruit, stem, vapor, runoff, nutrient solution, and eventually plant waste. Hydroponic or aeroponic systems may allow precise control, but precision creates its own dependence on pumps, nozzles, dissolved minerals, pH control, sterilization, and monitoring. Soil-like substrates may buffer some changes, yet they can hide others. Every agricultural method is a bargain between visibility, resilience, labor, and risk. In a closed world, contamination would be one of water's most patient dangers. A pathogen does not need drama to matter. A trace chemical can accumulate if the removal system does not recognize it. A cleaning agent useful in one compartment may burden a bioreactor elsewhere. Metals, plastics, medicines, hormones, industrial residues, and microbial byproducts could move through the loop in amounts small enough to miss at first. Over time, the ship would need not only recycling, but forensic memory, records of what entered the system, where it went, how it changed, and when it returned. The International Space Station can depend on replacement parts and resupply, even when those systems are expensive and complex. A generation ship cannot build its water discipline on that assumption. Membranes wear, pumps fail, seals crack, sensors drift, biological cultures shift, tanks need inspection, pipes gather films. A loop that worked for the launch generation may need redesign by the third or fourth generation, not because the founders were careless, but because no physical system remains identical to itself across centuries. Maintenance would be the loop's second bloodstream. A society shaped by this reality would probably teach water rules early. Children might learn which taps are safe, which fluids must never be mixed, why certain drains are not ordinary drains, why spills are reported rather than hidden, why washing has limits, and why a maintenance alarm near a recovery unit matters to everyone. This need not make childhood grim. Rules can become ordinary when they are consistent. A child raised aboard the ship might find open planetary wastefulness harder to understand than careful reuse. Custom would form around water as surely as engineering would. There might be ceremonies for the first independent harvest of a new generation, but the daily discipline would live in smaller habits. Cups not left unfinished, condensation reported, cleaning measured, medical fluids tracked, fabrication processes approved according to what they release into recovery streams. A person's private life would remain private in many ways, yet the chemistry of private life would still return to the common world. The ship would make that connection impossible to deny. Waste would carry another form of memory. The body gives back what it cannot use, and the ship asks what can still be taken from it. Carbon can return to agriculture. Nitrogen can return to nutrient cycles. Water can return to tanks. Some material can become feedstock for manufacturing or controlled biological processing. Other material must be isolated because usefulness does not erase danger. The ship's wisdom would lie in refusing both disgust and carelessness. Waste is not sacred. It is not worthless. It is a difficult resource with pathogens attached. Power again sits beneath the loop. Pumps, heaters, chillers, centrifuges, processors, sterilizers, compressors, sensors, and control systems all require energy. A water loop under energy stress may become less efficient, slower, or more selective about what it treats first. During a power shortage, drinking supply, medical use, crop irrigation, hygiene, cooling, and industrial work may compete in ways that reveal the true hierarchy of survival. A generation ship's politics could be exposed most clearly during water rationing, because rationing turns system design into social order. The first serious water crisis aboard the ship would likely enter history even if no one died. Perhaps a membrane failed in a way sensors did not catch quickly enough. Perhaps a contaminant moved from a workshop into a recovery stream. Perhaps a microbial bloom altered a storage tank. Perhaps a leak behind shielding remained small for too long before anyone found it. Once resolved, the incident would leave more than repairs. It would leave procedures, restrictions, teaching stories, design changes, and a new respect for whatever had almost been lost. A century later, descendants might know the crisis by name. They might not remember the fear exactly, but they would live inside its consequences. A valve added after the event, a rule against a certain solvent, a yearly inspection in a compartment most people never enter, a children's lesson about reporting moisture where moisture should not be. This is how technical memory becomes culture. The ship does not survive by avoiding every failure. It survives when failures are converted into forms of attention strong enough to outlast the people who experience them. There is a speculative possibility that the water aboard such a vessel would become emotionally charged in ways Earth cultures reserve for rivers, wells, and rain, not because the people misunderstand it, but because they understand it too clearly. A cup of water may have passed through a great-grandparent's breath, a crop leaf, a cooling line, a recovery membrane, a storage tank, and a child's soup before returning again. The chemistry would be ordinary. The continuity would not. In a closed world, Water makes ancestry physical. Still, sentiment cannot purify a tank. The ship would need testing, skepticism, replacement schedules, uncomfortable audits, and the freedom to correct old designs. If a revered recovery system begins to fail, reverence must not protect it from modification. If a traditional use of water becomes unsafe, tradition must yield. The loop must be loved through competence, not protected from knowledge. A civilization that drinks recycled water for centuries cannot afford mythology where measurement is required. Water also reveals why a generation ship can never be understood as a single invention. It is a chain of inventions continually repaired by a chain of people. The recovery system built at launch is only the first version of survival. Later generations may improve membranes, change crop water ratios, redesign waste treatment, discover contaminants the founders missed, or simplify a process that was too fragile. The loop remains alive because it is allowed to be worked on. Permanence comes through revision, not through freezing the original plan. By the time the ship is far beyond help from Earth, water discipline would have become part of its deepest identity. The people aboard would know, perhaps without saying it often, that nothing can be thrown away in the old planetary sense. There is only movement into another compartment, another process, another form, another risk. The vessel teaches this lesson with every drain and every cup. What leaves one life enters the system that supports another. Once air, food, and water have formed their loops, the ship has solved only the softer half of survival. Around those living cycles must stand a body strong enough to keep radiation out, pressure in, heat balanced, and micrometeoroid damage from becoming atmosphere loss. The next question gathers at the walls themselves, where mass becomes protection and deep space begins pressing against the thin artificial world inside. Chapter 6. Behind the shielding wall. Radiation would be one of the least visible conditions shaping life aboard a generation ship. A person could walk through a corridor, tend a crop tray, sit beside a sleeping child, repair a valve, or read from an old archive without sensing the particles passing through the vessel from outside. The danger would not announce itself through ordinary feeling. It would accumulate in cells, instruments, memory chips, blood-forming tissues, reproductive organs, and the quiet mathematics of probability. Deep space does not need to be loud in order to be severe. Earth had given human biology a shelter older than civilization. Its atmosphere absorbed much of the radiation that would otherwise reach the ground, and its magnetic field bent away many charged particles streaming from the sun. Human beings evolved beneath that protection, with bodies adapted to a planetary surface rather than open interplanetary space. Low Earth orbit weakens the shelter but does not remove it completely, because spacecraft there still pass partly within Earth's magnetic environment. A generation ship bound for interstellar distance would eventually leave that inherited protection behind. NASA's human spaceflight research treats radiation as one of the major hazards beyond Earth. The problem is not a single kind of exposure. Solar particle events can send intense streams of energetic particles outward from the sun, sometimes requiring astronauts to shelter behind available mass. Galactic cosmic rays are different. They arrive from beyond the solar system, include highly energetic nuclei, and are difficult to block without creating secondary radiation when they strike shielding. A ship on a years-long mission worries about dose. A ship crossing generations worries about dose becoming part of civilization. The first designers would therefore need to decide where the safest rooms belonged. A storm shelter could be placed near water tanks, food stores, fuel mass, or other dense supplies so that necessary material also served as protection. Sleeping areas might be arranged closer to the vessel's protected core. Nurseries, medical rooms, reproductive storage, and command systems might be shielded more heavily than ordinary corridors. The layout of the ship would become a map of biological priority. Architecture would show what the builders feared most. Shielding sounds simple until mass enters the calculation. More mass usually means more protection, but every kilogram must be built, launched, assembled, accelerated, slowed, supported, cooled, repaired around, and justified against other needs. Water is attractive because the ship already requires it, and because hydrogen-rich material can help reduce some radiation risks. Polyethylene and other hydrogen-rich substances have also been studied for shielding. Regolith, or slag from asteroid processing, might be useful if the ship were assembled with access to extraterrestrial material. Yet protection never arrives as a free wall. It always arrives as a trade. Behind such shielding, the inhabited world would feel shaped by thickness. The safest quarters might not be the most open or beautiful. They might be low, central, wrapped in tanks and stores, with fewer windows or none at all. A corridor could bend around a water reservoir not for aesthetics, but because the reservoir stood between children and particles no eye could see. Mass would press into the design like a silent geography. The ship's deepest rooms would owe their calm to all the material gathered between bodies and space. There would be no perfect wall. Galactic cosmic rays are difficult precisely because some carry so much energy that ordinary shielding cannot stop them cleanly. When a high-energy particle strikes material, it may produce showers of secondary particles that create their own biological and electronic concerns. That does not make shielding useless. It makes shielding a matter of balance, choosing materials, thickness, geometry, and shelter protocols that reduce risk without making the vessel impossible to move. The safe answer is not infinite mass. The safe answer is the best compromise a civilization can afford to carry. Electronics would have their own vulnerability. Radiation can flip bits, degrade components, damage detectors, and shorten the useful life of systems that control navigation, life support, medicine, agriculture, and communication. A generation ship could not rely only on delicate machines behaving perfectly for centuries. Critical computing would need redundancy, error correction, hardened components, backups held offline, and the ability to manufacture or rebuild parts when old ones failed. The ship's memory would not be only cultural, it would also be electrical, and radiation would keep testing it. The first solar particle event after departure might become one of the early stories aboard the vessel. The sun would still be close enough to matter, and the warning systems would carry their own authority. People would move toward protected compartments, not in panic if training held, but with the practiced seriousness of a community that knows why doors close. Farms might be placed in safe mode. Non-essential work might stop. Medical staff would confirm who had reached shelter. The event would pass into logs as dose, duration, warning time, shielding performance, and human response. A century later, descendants might study that event without feeling its original urgency. They would see diagrams, records, perhaps recordings of voices instructing families through the procedure. A child might learn that a certain corridor was reinforced because of what happened during that early storm. The sun that caused it may no longer dominate daily imagination if the ship has moved far away, but the rule would remain. Radiation events become history when they pass. Radiation risk remains engineering when history forgets the fear. Farther from the sun, solar events would diminish, but galactic cosmic rays would remain. The ship would not be crossing an empty tunnel. It would move through a universe filled with high-energy particles whose sources include supernova remnants and other energetic astrophysical processes. These particles arrive at the vessel as part of the background condition of space. They are not aimed at it. They do not notice it. Their indifference is part of the problem, because no negotiation is possible with a hazard that has no local cause. Biology responds to radiation through damage and repair. Cells can mend many kinds of injury, but not all, and not always correctly. DNA damage, cancer risk, cataracts, degenerative tissue effects, fertility concerns, pregnancy risk, immune changes, and possible nervous system effects all become part of the medical landscape. A ship whose voyage lasts centuries would need to think not only about protecting adults during one career, but about protecting embryos, children, pregnant bodies, stored genetic material, and the long health of a small population. Radiation becomes demographic when time is long enough. Medical records would therefore carry more weight than they do on Earth. Dose history might be tracked from birth. Work assignments could consider accumulated exposure. People who repair outer systems might face different lifetime limits from those who work in core compartments. A person's right to choose dangerous maintenance work could come into tension with the population's need to preserve health and expertise. These are uncomfortable questions, but sealed civilizations cannot leave all risk to private preference. One person's exposure may later become a family's grief, a medical burden, or a lost skill. Stored embryos, gametes, seeds, microbial cultures, and genetic archives would need shielding too. The future aboard a generation ship would not exist only in living bodies. It would be kept in freezers, vaults, culture banks, seed libraries, and protected records. Radiation damage in those stores might be subtle until the material was needed. A seed that no longer germinates, a corrupted genetic record, a weakened cell line, or a damaged archive could reveal a failure from decades before. Protection for the unborn and ungrown would have to be designed without the emotional immediacy that living passengers naturally receive. The outer hull would face a different kind of exposure. Shielding meant to protect biology also has to survive radiation, thermal cycling, dust impacts, and the slow aging of material. Layers may become brittle, sensors may degrade, adhesives may change, insulation may lose performance. A shield is not only a passive mass placed once around a world, it is a maintained boundary. If it cannot be inspected, patched, monitored, and understood by later generations, its original thickness may become less reassuring than its drawings suggest. Some designers have considered magnetic or plasma shielding concepts, borrowing from the fact that Earth's magnetic field helps shape the charged particle environment around the planet. Such systems remain speculative for a large human vessel, especially because they require power, field strength, stability, and interaction with a complex radiation environment. They may reduce some charged particle exposure, but they would not remove the need for material shielding. A generation ship would likely distrust any single elegant answer. Its survival would come from overlapping protections, none complete alone. Social life would adjust around the wall. People may speak casually about the core, the outer decks, the shelter bands, and the high exposure work zones. Housing assignments might carry prestige or resentment depending on who receives the better shielded areas. Children might be taught not to linger near certain compartments during alerts. Maintenance crews might rotate through exposed duties with strict records. The ship's geography would not be neutral. Radiation would write hierarchy into distance from the hull unless the society worked carefully against it. Even windows, if the vessel had them, would become complicated symbols. The large, transparent view into space is emotionally powerful and technically costly. Transparent materials can be weaker, heavier, harder to shield, and more vulnerable than solid walls with cameras. A ship built for centuries might prefer screens fed by external instruments, giving people images without opening unnecessary weaknesses in the protective mass. The loss would be real for the first generation, who remembered looking through air. Later generations might not feel it as loss. They might trust mediated sight because their world had always seen through instruments. The shielding wall also changes the meaning of outside work. Any repair beyond the protected layers would require planning around dose, duration, suit reliability, and the possibility of particles arriving without concern for human schedules. Robots would likely perform much of the dangerous work, but robots need maintenance, control, parts, and recovery when they fail. A human stepping into a high-exposure zone would not be entering adventure. They would be spending a limited biological allowance. The ship would count that expense carefully. Across centuries, radiation would become part of the vessel's calendar. Periods of higher exposure, recorded events, shield inspections, component replacements, medical screenings, and archive checks might create rhythms that seem ordinary to those born inside them. The danger would remain real, but familiarity would soften its emotional edge. That softening is useful because fear cannot govern every hour. It is also dangerous because invisible hazards are easiest to ignore when routine has domesticated them. The best generation ship would not eliminate radiation risk. It would make the risk survivable, measurable, distributed, and remembered. It would carry mass where mass mattered, move people into shelter when warning allowed, harden the machines that governed life, protect the genetic future, and teach each generation why invisible particles deserved visible rules. Survival would depend on a culture that believed numbers before symptoms, records before rumor, and maintenance before comfort when the wall required attention. Beyond the shielding, deep space would continue without hostility and without mercy. Inside it, the ship's people would sleep, work, eat, age, and measure their children against marks on clinic walls. Between those bodies and the particle rain would stand water, polymer, metal, fuel, stores, structure, warning systems, procedures, and the accumulated caution of the dead. The wall would not make the vessel safe in any absolute sense. It would make life possible long enough for the next problem to gather slowly in the materials of the ship itself. A shield can reduce what enters from outside, but it cannot stop time from working inside the vessel. Pumps cycle, bearings wear, seals harden, circuits age, panels fatigue. Machines designed by one generation become the inheritance of another, and the ship's survival begins to depend on whether its people can keep repairing the body that protects them. Chapter 7: The Slow Aging of Metal. Metal remembers use in ways people do not always notice. A pressure ring holds for years, then shows a hairline change along a seam. A bearing turns through millions of quiet cycles before its surface begins to lose its original smoothness. A seal that once flexed easily grows less forgiving after long exposure to heat, cold, radiation, vibration, and chemical traces in the air around it. A generation ship may look permanent from the inside, especially to those born beneath its ceilings, but every material aboard it would be participating in time. The ship's living systems would depend on that material patience. Air loops need ducts, housings, valves, fan blades, filters, sensors, and pressure doors. Water loops need pumps, membranes, tanks, pipes, joints, and inspection ports. Farms need trays, lamps, wiring, nutrient lines, root supports, harvest machines, and sterilization equipment. Medical rooms need scanners, surgical tools, cold storage, sterile surfaces, and diagnostic instruments. None of these objects is immortal. Even when a machine is not broken, it is always becoming slightly more used than it was before. Spacecraft engineering already understands this in shorter missions. A component is not judged only by whether it works on the day of launch. It is tested through vibration, vacuum, radiation, thermal cycling, load, fatigue, and failure probability. Designers ask how it behaves when shaken, heated, cooled, powered on, powered off, exposed to particles, and forced to endure conditions unlike the room where it was built. A generation ship extends that question until it becomes almost civilizational. A part must not only work, it must be inspectable, repairable, replaceable, understandable, and teachable. Fatigue would be among the vessel's quiet enemies. A structure can fail after repeated stress, even when each individual stress remains below the level that would break it at once. Small loads return again and again. A hatch opens. A pump starts. A radiator panel expands under heat and contracts as it cools. A rotating habitat holds its shape under continuous tension. The danger does not require drama. It only requires cycles. And a ship meant to last centuries would be built from cycles layered upon cycles. Rotating sections would make this especially important. If the ship uses spin to create artificial gravity, the structure must carry loads without interruption. Bearings, magnetic supports, joints, vibration dampers, seals between rotating and non-rotating sections, and power transfer systems all become part of the body's hidden skeleton. A child walking along the inner curve of the habitat might feel only floor beneath their feet. Engineers would know that floor as a moving agreement among stress, mass, radius, and maintenance history. The surface of old machinery would develop a practical language. A slight discoloration near a joint might suggest heat. A powdery trace might point toward abrasion. A change in sound could reveal imbalance before a gauge does. The feel of a panel under a gloved hand, the resistance of a latch, the unexpected warmth of a housing, the fine grit found inside a service cover, all of these would matter. A ship that cannot read its own surfaces is already becoming less safe. Radiation would add another layer of aging. Electronics can be damaged by energetic particles, not always through obvious destruction, but through bit flips, gradual degradation, leakage currents, and weakened performance. Insulators can change. Optical sensors can darken. Memory can corrupt. Semiconductors may continue functioning while becoming less trustworthy. The vessel's intelligence, distributed through processors and control systems, would need constant checking against itself. A machine that gives wrong numbers with confidence can be more dangerous than a machine that refuses to answer. For that reason, the ship would need generations of diagnostic discipline. Sensors would watch other sensors. Control systems would compare readings across redundant paths. Archives would hold older baselines so that slow drift could be recognized. A temperature sensor that reads slightly low for 20 years may train people to accept a false normal. A pressure gauge that shifts within tolerance can still mislead if many such shifts align in the same direction. Maintenance is not only repair after failure, it is the art of noticing when the definition of normal has begun to move. Micrometeoroids and dust would leave their own signatures. Even tiny particles can matter at high speed, and a vessel crossing enormous distances cannot assume that rarity equals safety. Outer layers might be designed to absorb, fragment, or spread impact energy before pressure walls are threatened. Whipple shields and layered barriers offer one practical principle: do not depend on a single skin where a sacrificial outer layer can help break and disperse an incoming particle. The ship's exterior would therefore carry scars that never entered daily conversation, except in inspection logs and repair schedules. Repair outside the protected interior would be one of the vessel's most delicate forms of labor. Robots might crawl along hull tracks, replace panels, inspect shield layers, weld patches, test sensors, or carry small tools into zones where human exposure would be costly. Yet robots also age. Motors wear, cameras degrade, joints stiffen, batteries weaken, software accumulates patches, and replacement parts must come from somewhere inside the same closed economy. Automation can reduce risk, but it does not remove the need for a society that knows how its helpers are made. Manufacturing aboard the ship would have to be more than a convenience. Spare parts stocked at launch may cover predictable failures for a time, but centuries punish inventories. Some parts will be used faster than expected. Others will become obsolete after systems are redesigned. Materials may degrade in storage. Documentation may outlast the machines it describes, or machines may outlast the people who understand the documentation. A mature generation ship would need workshops able to cut, print, cast, sinter, machine, test, and certify replacement components from available feedstock. This creates a second loop beside air, water, and food. Material must also circulate. Broken parts become scrap. Scrap becomes sorted stock. Sorted stock becomes new parts. Shielding filler, tools, brackets, housings, or structural patches. High-grade materials would be guarded carefully because not every alloy or electronic component can be recreated easily inside a ship. The vessel might have warehouses that feel less like storage rooms than mineral banks. A drawer of rare connectors could matter as much as a seed vault. Polymers would bring their own difficulties. Plastics, rubbers, adhesives, coatings, insulation, gaskets, and flexible tubing make modern engineering possible, but many of them age in ways that are harder to forgive than metal. They can embrittle, outgas, crack, absorb chemicals, lose elasticity, or change under radiation. A seal may look intact until pressure tests reveal its weakness. Cable insulation may become fragile in a compartment opened only during rare maintenance. The soft parts of the ship might decide the fate of hard systems. Lubrication would also be a long-term problem. Moving parts need surfaces that can slide, roll, or turn without destroying themselves too quickly. In vacuum, under radiation, or across wide temperature ranges, ordinary lubricants may evaporate, thicken, separate, or become contaminated. Bearings may use specialized materials, magnetic suspension, dry lubricants, or sealed assemblies. But every method carries limits. A quiet rotating part that has worked for 200 years may still be approaching a form of wear no one living has ever witnessed firsthand. The ship's archives would need to preserve failure knowledge with unusual care. Not all failures are equal, and not all repairs should be repeated. A patch that saved one compartment in year 30 might be dangerous if applied to a different system in year 200. A temporary bypass can become permanent through forgetfulness. A clever improvisation can enter tradition after the original risk is forgotten. Maintenance records must therefore include context, not only instruction. Descendants need to know what was done, why it was done, what was not known, and which later inspections confirmed or corrected the decision. A culture of repair would likely form around apprenticeship. Some knowledge can be stored in manuals, diagrams, simulations, and diagnostic programs, but hands still matter. The pressure needed to seat a component, the sound of a healthy pump, the smell of overheated insulation, the pace at which a vacuum chamber should stabilize, the difference between surface corrosion and harmless staining. These are learned through contact with real systems. On a generation ship, craft would not be nostalgic. It would be survival passing through muscle memory. This craft could easily become social power. Those who understand the ship's old systems would hold knowledge everyone else depends on. If repair guilds become too closed, the society risks technical priesthood. If knowledge is spread too thinly, competence may weaken. The ship would need to honor expertise without allowing expertise to become ownership of the world. A person who can repair the air system is necessary. A class that can threaten the air system through monopoly is dangerous. Standardization would help, but only to a point. Common parts, modular panels, shared fasteners, interchangeable pumps, and unified diagnostic ports make repair easier. Yet too much uniformity creates shared vulnerability. If every pump uses the same seal, one seal problem becomes a ship-wide problem. If every controller depends on the same chip family, one radiation weakness may travel everywhere. The designers would have to balance the efficiency of sameness against the resilience of difference. Later generations would continue that balance with less access to the original industrial base. There may be rooms aboard the ship dedicated to old parts that no longer fit anything current, kept because no one dares discard material that once mattered. There may be shelves of obsolete circuit boards, old actuator housings, pump casings from early redesigns, cracked ceramic insulators, retired sensor arrays, and printed manuals with corrections layered across margins. Such places would not be museums in the decorative sense. They would be memory stores for the hands. A failed part can teach what a clean diagram cannot. Fire would remain one of the most feared material events. In a closed vessel, combustion is not just heat and flame. It is smoke, toxic gas, oxygen consumption, surface damage, panic, and contamination of air systems. Material choices would be shaped by flammability, off-gassing, melting behavior, and cleanability. Workshops and kitchens, fabrication bays and battery rooms, crop areas and medical storage would all carry different fire risks. The ship would need suppression systems that protect life without poisoning the loops that life depends on afterward. Thermal management would age too. Heat has to go somewhere. Electronics, bodies, lamps, reactors, motors, pumps, and processors all produce it. Radiators release heat into space, but radiators can be damaged. coated with dust, shadowed by design changes, or degraded by material fatigue. Internal heat exchangers can foul, coolant lines can leak. A small decline in thermal performance can force machinery to run hotter, which can shorten its life, which can create more failures. Temperature becomes a slow conversation among nearly every system aboard. The long voyage would also punish documentation formats. A maintenance manual stored digitally must remain readable by future hardware. A diagram printed on durable material must remain accurate after modifications. A simulation used for training must be updated as systems change, or it becomes a beautiful lie. The ship's technical memory would need curators who understand that an archive is not safe just because it exists. A record must be legible, trusted, revised, backed up, and connected to practice. For those born late in the journey, the ship may appear ancient in the way mountains appear ancient on Earth. Its walls were there before grandparents. Its oldest maintenance shafts might carry dates that feel almost mythic. Some systems may have been rebuilt so many times that no original component remains, while the name of the system persists. Other components may still be original, protected by low use or careful design, and treated with caution because no one is certain how to replace them perfectly. The vessel becomes old unevenly. That uneven aging may decide how long the ship can survive. A generation ship does not fail when everything wears out at once. It fails when enough connected systems lose margin together. A tired pump strains a power bus. A power shortage reduces water recovery. Reduced recovery stresses agriculture. Agriculture changes atmospheric balance. Atmospheric stress increases medical demand. Medical demand consumes supplies and labor. The web tightens. Survival depends on keeping failures local before they become ecological. There is no final repair that solves this forever. Each generation receives a vessel already marked by earlier work and passes it onward with new marks added. The most successful ship may not be the one that preserves its original form, but the one that can change without losing its ability to understand itself. Panels may be replaced. Farms may be rearranged. Control systems may be rewritten. Shielding may be patched. Whole compartments may change purpose. Continuity would live not in untouched material, but in the disciplined renewal of material. A machine crossing deep space for centuries would therefore become a history of hands. The hands that tightened the first launch assemblies. The hands that replaced early filters. The hands that repaired a crack before it widened. The hands that taught a child how to read vibration through a tool. The hands that recycled a broken bracket into a new latch. None of these gestures would be enough alone. Together, repeated beyond memory, they would become the ship's answer to time. Once the vessel can breathe, feed, recover water, shield its people, and repair its own body, another question begins to grow inside it. Machines can be maintained by training, but human continuity has its own rules. Children will be born into the transit world. They will inherit obligations before they understand them, and their lives will determine whether the ship remains a mission, becomes a society, or slowly turns into something no founder could have fully imagined. Chapter 8. Children of the Transit Years. Children born aboard a generation ship would enter the voyage without ever having chosen it. They would arrive inside a world already moving, already governed by old promises, already shaped by procedures written before their birth. Their first air would be recovered air. Their first horizon might be the curve of a rotating habitat. Their first lessons about danger would not concern traffic, weather, wild animals, or open water. But pressure doors, sealed compartments, warning tones, crop health, radiation shelters, and the meaning of a vent that had stopped breathing properly. For them, deep space would not be an adventure. It would be the condition into which childhood had opened. The first adults would understand this difference with a tenderness that might also carry guilt. They had memories of Earth, or at least memories of preparation near Earth, and they had accepted the voyage through training, selection, duty, belief, fear, necessity, or hope. Their children would inherit the result. No contract signed before launch could truly include them. No founding ceremony could ask permission from those not yet alive. A generation ship therefore begins its moral difficulty the moment its first child is born, because survival now depends on people whose lives are not extensions of the founder's consent. Biology would not pause for philosophy. Infants would need safe gestation, birth care, nutrition, immune protection, developmental monitoring, and stable gravity conditions. If the ship used rotation to create artificial gravity, pregnancy and childhood would occur under an engineered approximation of what human bodies evolved to expect. Too little gravity could threaten bones, muscles, balance, and development. Too much spin, or too small a radius, could create motion-related problems that adults might tolerate better than children. The nursery would be one of the ship's most scientifically watched spaces, not because children are experiments, but because the future population passes through their bodies first. A child would learn the ship through repetition before explanation. The hum of circulation would belong to sleep. The measured brightening of lamps would become morning. A parent's hand on a corridor rail would teach movement along a curved floor. Meals would arrive from crop rooms and processors whose names might be familiar before their mechanisms were understood. Somewhere near the edge of ordinary life, warning drills would shape behavior: how to move toward shelter, when to wait, which doors not to open, whose instructions override confusion. Safety would enter the body as habit before it entered the mind as knowledge. Education aboard the ship would carry a different weight from education on Earth. Reading would preserve archives. Mathematics would support repair, navigation, medicine, agriculture, power management, and population planning. Biology would not be a school subject alone. It would explain food, waste, air, infection, reproduction, and the hidden labor of microbes. History would not be decoration. It would tell children why their world was built, what failures had nearly ended it, which decisions remained disputed, and why some rules had outlived the people who wrote them. A poorly educated generation would not merely be less informed, it could become dangerous to itself. The first schoolrooms might still use Earth as the central reference. Lessons would show oceans, mountains, forests, deserts, cities, animals, weather, and open sky. Teachers might say that rivers flow downhill, though no child had seen a river except in recordings. They might explain rain, though water aboard the ship returned through condensers and pipes. They might describe a horizon, though the child's world curved inward. Each lesson would have two layers: the fact itself and the loss of direct experience beneath it. Earth would be taught as origin before it could be remembered as home. Later generations would require a different education. If Earth becomes too sacred, the shipborn may feel like exiles from a world that rejected them before birth. If Earth becomes too distant, the mission may lose its emotional center. Teachers would need to preserve planetary knowledge without making ship life feel like a lesser copy. A child cannot live well inside a world that every lesson describes as second best. The curriculum would have to say, in careful ways, that Earth was the beginning, while the vessel remained the present responsibility. Isolation studies on Earth can only help a little. Antarctic winter overstations, submarines, remote research bases, and long-duration space missions all show something about confinement, routine, small groups, delayed communication, and dependence on life-supporting systems. None of them fully resembles being born, growing up, choosing work, loving, aging, and dying inside a sealed interstellar habitat. The analogues are useful because they reveal stress points. They are limited because the people inside them still know that a larger world continues outside the mission. A ship-born child would not carry that same reassurance. The larger world would exist as knowledge, not access. Earth might be alive, altered, unreachable, or politically irrelevant by the time the child learned its name. The destination might be centuries ahead. The child's real community would be finite enough to know by reputation, structured enough to feel watchful, and fragile enough that private rebellion could become public risk. Growing up would mean discovering that personal freedom existed inside systems that could not be allowed to fail. This does not mean childhood aboard the ship would have to be joyless. Children create play within almost any boundary. A maintenance corridor becomes a route of secret importance. The crop chamber becomes a place of smells, textures, forbidden shortcuts, and seasonal anticipation. A low-gravity training compartment, if one exists, becomes a source of games adults pretend not to enjoy. Old Earth animals preserved in video may become favorites. A festival timed to a harvest, a ship anniversary, or the crossing of some navigational marker could give the year shape. Constraint does not erase play, it changes the materials from which play is made. Still, every joy would live beside planning. Birth rates could not be left entirely unmanaged. A generation ship must maintain enough people to preserve labor, knowledge, genetic diversity, caregiving, defense against accidents, and social life. It must not grow beyond food, water, space, medical capacity, and psychological tolerance. Reproduction would therefore become one of the most delicate political subjects aboard. Too much control would injure human dignity. Too little control could endanger everyone. The society would need rules that are legitimate before crisis forces them into cruelty. Families might look different under such conditions. Some children could be raised by biological parents, others by wider kin groups, professional caregivers, or educational cohorts designed to distribute attachment and responsibility. Work schedules, radiation exposure, medical risk, genetic planning, and population balance might all affect family life. Stored embryos or gametes could complicate ancestry, allowing future births from genetic lines preserved before launch. A child might belong to living parents, archived ancestry, and the ship itself in ways that planetary law had never fully imagined. Adolescence would test the vessel's culture sharply. Young people must eventually question inherited rules, and a society that cannot survive questions is brittle. Yet aboard a generation ship, some rules protect air, water, food, radiation safety, and demographic stability. The challenge would be teaching the difference between laws that deserve revision and constraints that physics will not negotiate. A teenager may reject a tradition. They cannot reject carbon dioxide limits without consequence. Mature governance would need spaces for dissent that do not turn life support into a bargaining tool. Work inheritance could become another pressure. A small society cannot allow every person to choose freely without regard to needed skills, but it also cannot reduce children to assigned functions without deforming them. The ship would need engineers, farmers, doctors, teachers, archivists, fabricators, waste system specialists, software maintainers, caregivers, radiation monitors, navigators, and mediators. Aptitude would matter, desire would matter, so would duty. The fairest system might still feel unfair to someone whose dream does not match the vessel's requirements. The first generation might speak of the destination with urgency. Their children might repeat that urgency out of loyalty. Their grandchildren might ask harder questions. What does it mean to devote a life to a planet no living person has seen? What if the target is unsuitable? What if the ship itself is safer than arrival? What if the mission was launched under assumptions that later knowledge has weakened? These questions would not mean the young had betrayed the voyage. They would mean the voyage had lasted long enough to become subject to history. Psychological health would be inseparable from meaning. A child raised only to preserve systems may grow into resentment. A child raised only on myths of destiny may be unprepared for technical reality. The culture would need stories honest enough to bear disappointment and practical enough to support work. It would need art, music, games, grief rituals, humor, privacy, friendship, and forms of beauty not reducible to mission efficiency. Human beings do not survive as machines that happen to eat. They survive as bodies inside meaning. The ship's designers might try to provide parks, open communal spaces, varied light cycles, soundscapes, art walls, libraries, and simulated environments. These would help, but simulation has limits. A recorded forest is not a forest. A projected ocean is not wet unless water is spent to make it so. A ceiling that shows clouds does not carry weather. Over time, however, shipborne people may not experience these things as false in the same way their ancestors would. A copied sky can become a real childhood memory if it is the ceiling under which a person first felt safe. Language would begin adjusting around such experiences. Words brought from Earth might change meaning. Outside could mean beyond a compartment rather than outdoors. Weather could refer to humidity cycles or agricultural climate settings. Morning could be a lighting schedule. Ground could be the inner hull. Far could mean several decks away for a child, then light years away in a lesson. Every generation would speak the old language into a new arrangement of reality. Slowly, the ship would begin to sound like itself. The adults responsible for these children would face a hard balance between protection and honesty. Too much fear could make life feel like a sentence. Too much comfort could hide the fragility that discipline must protect. Children need to know that the hull matters, but not feel that death waits behind every wall. They need to understand the mission, but not be crushed by the fact that ancestors chose it for them. They need affection that is personal, not merely civilizational. A child cannot be loved only as the future of the species. There would be losses no design could erase. No child aboard the ship would run through unbounded weather. No one would wander away from the world and return at dusk across open land. Large animals might exist only in archive, small managed populations, or genetic storage. The night sky, if shown, would be mediated through cameras and screens, filtered by the same walls that kept the child alive. These absences would be clearest to those who remembered Earth. To those born later, the sorrow may belong more to stories than to experience. Yet the children of the transit years would also possess forms of intimacy Earth rarely teaches so plainly. They would know that air is shared. They would know that water returns. They would know that food is labor made edible. They would know that a wall can be the difference between ordinary sleep and catastrophe. They would know that old repairs matter. They would know that the dead remain present through systems maintained in their names. Their world would be small, but its connections would be visible. As generations pass, the ship's survival would depend less on the courage of the founders and more on the steadiness of those who never saw launch. The children born in transit would become the adults who decide which rules to keep, which machines to rebuild, which stories to teach, which births to plan, which risks to accept, and which inherited assumptions to question. The generation ship survives only when the unborn become caretakers without being treated as tools of the past. Beyond childhood waits a narrower problem, one that cannot be solved by education alone. A ship may teach its young well and still fail if the population is too small, too genetically fragile, too socially divided, or too poorly balanced across age and skill. The vessel must remain a world of persons, but it must also remain a population counted across births, deaths, ancestry, risk, and time. Chapter 9. A population small enough to count. A generation ship would carry people as carefully as it carried water, seeds, medicine, and air. The population could not be treated as a crowd that happened to live inside the vessel. It would be one of the vessel's central systems, though never only a system, because every number in that system would have a name, a body, a childhood, a family, a grief, and a future. Too few people, and the ship risks genetic narrowing, labor shortages, social exhaustion, and the loss of rare skills. Too many people, and the ship begins to press against food, space, water, medical capacity, psychological tolerance, and the delicate loops that keep everyone alive. There is no single safe number for a generation ship. Any exact figure would depend on voyage length, medical technology, genetic diversity, stored reproductive material, catastrophe planning, governance, age structure, and the reliability of the habitat itself. A ship traveling for 100 years would face a different population problem from one traveling for 500. A vessel with large frozen genetic reserves would differ from one relying only on the people alive at launch. A society able to manufacture medicines, correct some hereditary risks, and maintain detailed reproductive records would have different margins from one that loses those capacities. Population is not a passenger count, it is a long equation written through generations. Population genetics gives the first warning. A small founder group carries only part of the genetic variation of the larger population from which it came. Through chance alone, some traits become more common, others disappear, and harmful recessive conditions can become harder to avoid if ancestry lines are too closely connected. Genetic drift does not need intention. It works through births, deaths, pairings, accidents, disease, and the ordinary randomness of who has children and who does not. On Earth, movement among populations can soften these patterns. Inside a ship, no new village waits over the hills. That closed ancestry would make record-keeping essential. The ship would need to know who descended from whom, which genetic risks were present, which lines were underrepresented, which pairings carried elevated danger, and how future diversity might be protected without turning human intimacy into mechanical allocation. A simple family tree would not be enough after many generations. The record would need medical detail, reproductive history, stored genetic material, and changing knowledge as later doctors understood conditions earlier doctors could not name. Genealogy would become public infrastructure, though not all of it could be public without harming trust. Here, the ship enters one of its hardest moral corridors. Reproduction aboard a closed vessel cannot be purely private in the way many planetary societies imagine it, because each birth changes the balance of the world, yet people are not livestock, and no society that treats them that way deserves to call survival a success. The laws around birth would have to be legitimate, transparent, revisable, and humane long before shortage or panic made them severe. The community would need to decide how many births the ship can support, how risks are discussed, how exceptions are handled, and how dignity survives inside planning. Age structure would matter as much as total population. A ship with many children and too few trained adults could strain education, food supply, and medical care. A ship with many elders and too few young workers could lose maintenance capacity. A sudden decline in births might not seem dangerous at first, then create a labor and caregiving crisis decades later. Too many births after a period of fear could produce a different imbalance. Demography moves slowly enough that mistakes can look harmless while they are being made. By the time the shape is visible, the people who caused it may already be old. A population officer, council, or statistical system might track these patterns with unusual seriousness. Birth cohorts, skill cohorts, medical needs, training pipelines, retirement expectations, radiation exposure histories, and family structures would all become part of planning. The ship would need engineers 20 years from now, not only today. It would need surgeons 30 years from now, agricultural specialists in every generation, teachers before every large childhood cohort, and enough general competence that a single accident could not remove an entire field of knowledge. A missing profession can become as dangerous as a broken pump if no one remains who knows how to repair it. Stored embryos, sperm, eggs, or broader genetic libraries could widen the future beyond the living founder population. Such reserves would not solve everything, but they could reduce genetic narrowing and preserve variation for later generations. They would require shielding, cooling, monitoring, power, legal rules, medical skill, and cultural acceptance. A child born from a genetic line stored before launch might have no living parents in the ordinary sense, or might be raised by parents whose biological relation differs from social relation. The ship would need family law flexible enough to protect children without making ancestry feel like a technical transaction. Even with genetic reserves, catastrophe planning remains necessary. Disease could reduce population. A radiation event could affect fertility or health. A fire, crop failure, manufacturing accident, Political conflict or medical shortage could remove people from critical age groups or professions. The population must have enough margin to absorb loss without collapsing into emergency reproduction or forced labor. In conservation biology, the danger of a bottleneck is not only that a population becomes small, it is that smallness removes options. A generation ship would fear that narrowing in bodies, skills, and choices alike. The spatial experience of such a population would be unlike city life. A vessel might contain thousands, perhaps tens of thousands if large enough. But even then, the society would be finite in a way most planetary people rarely feel. Reputation would travel quickly. Family histories would be known. Old conflicts might echo because there is no distant province into which a person can fully vanish. Marriage, friendship, disagreement, mentorship, and rivalry would all happen under the knowledge that escape from the society is impossible. A population small enough to plan is also small enough to remember. That memory could protect the ship. People might know who is isolated, which family is grieving, which apprentice needs support, which technician is overworked, which elder carries knowledge not yet transferred, which young person shows unusual ability. The same closeness could also wound. Privacy would be difficult to defend in a world where reproduction, health, work, and ancestry carry communal consequences. A society aboard a generation ship would need unusually strong customs around confidentiality. Without them, demographic planning could become social surveillance. Marriage and partnership would carry layers of meaning beyond affection. Some pairings might be discouraged for genetic reasons. Some families might be asked to consider delayed childbirth. Others might be encouraged to have children because a line is underrepresented or a cohort is too small. If stored genetic material is used, parenthood may include choices between love, duty, medicine, and law. A humane ship culture would need to protect the emotional reality of family from being swallowed by population arithmetic. People may accept limits more readily when the limits are explained, shared, and not applied only to the powerless. Genetic technology could change the picture, but not erase it. Screening for severe hereditary conditions might help. Gene editing, if safe and accepted by the society, could reduce some risks. Artificial wombs, if they existed and worked reliably, could change the burden of pregnancy and allow population planning under different medical conditions. None of these tools removes the central difficulty. Tools require trust, skill, energy, materials, repair, and governance. A technology meant to protect future children can become a source of fear if people believe it is used to design obedience, status, or class. The ship would also need to guard against social bottlenecks. Genetic diversity is not enough if thought narrows. A population that preserves healthy bodies but loses intellectual variety may become unable to adapt. Dissent, experiment, artistic expression, philosophical disagreement, and scientific revision all have survival value in a changing vessel, yet too much factional division can threaten the cooperation required by life support. The ship would need a culture that allows argument without letting argument become sabotage. That may be harder than keeping a pump running, because human conviction does not come with calibration marks. Small societies often develop intense norms because survival depends on predictability. On a generation ship, those norms might concern work schedules, food use, reproduction, education, maintenance, grief, privacy, and authority. Norms can preserve life by making good behavior automatic. They can also trap people inside expectations no one remembers choosing. After centuries, a rule created during a temporary crisis might still shape who may marry, who may train for command, who may enter certain professions, or who is trusted with archives. Population survival would require not only continuity, but periodic moral inspection. The children of each generation would eventually discover that they are not only loved individually, but also counted collectively. That discovery could be painful. A child might learn that their birth occurred during a planned cohort expansion. Another might learn that their parents had to petition for permission. Someone else might be born from stored genetic material chosen to restore diversity. These facts need not diminish love, but they would alter the story of origin. The ship's language around birth would therefore matter. If people are spoken of as quotas, resentment will grow. If planning is hidden, trust will decay. If truth is handled with care, duty may become bearable. Aging would shape the population's emotional life as strongly as birth. Elders aboard the ship would be more than retired workers. They would hold experience of older configurations, older failures, older customs, and perhaps older versions of the mission itself. Their bodies might need care that draws heavily on younger labor, but their knowledge could prevent repeated mistakes. The society would need to value them without allowing memory to harden into veto power over necessary change. A ship that worships age may become unable to adapt. A ship that discards age may repeat preventable errors. Death inside the vessel would return the body to the closed world in practical and symbolic ways. Burial in soil would be unlikely if space and biological control were limited. Cremation would consume energy and affect air systems. Chemical or biological processing might recover water, carbon, minerals, and other material. Every option would carry emotional weight. The dead could not be released into an unlimited earth. They would remain in some form, inside the same material economy that held the living. A culture would need rituals that honor grief while accepting that closed life asks even death to rejoin the loop. Population size also affects governance. A very small ship might rely on direct deliberation, but personal closeness could make impartial law difficult. A larger ship might develop councils, courts, departments, professional classes, and political factions. The number of people determines how authority feels. With hundreds, everyone may know the leaders too well. With thousands, institutions can gain distance. With tens of thousands, the ship may begin to resemble a small city-state, but one whose borders are pressure walls and whose economy cannot expand outward. Every scale solves one problem while creating another. Conflict would be inevitable. People may disagree about destination, reproduction rules, resource use, inheritance, labor duties, archive interpretation, or the rights of shipborne generations to revise the founding mission. A population small enough to count cannot afford civil rupture, but forbidding conflict would only drive it underground. The ship would need courts, mediation, elections or other legitimate procedures, protected speech, emergency limits, and ways to restore trust after harm. Justice aboard the vessel would not be abstract. A punished person still breathes the same air and may repair the same systems as those who judge them. The possibility of caste would have to be resisted from the beginning. If certain families become associated with command, others with farming, others with waste systems, others with dangerous hull work, the pattern may begin as practical continuity and end as inherited inequality. Technical apprenticeship can easily become social enclosure. Genetic planning could be misused to justify rank. Radiation exposure records could create groups seen as less desirable for reproduction. The ship's population system would need safeguards against turning survival planning into a hierarchy of human worth. There is also the risk of demographic myth. A founding population might be remembered as pure, brave, chosen, or uniquely wise. Their descendants might use that memory to justify policies the founders never intended. Families descended from early officers might claim authority through ancestry. Groups born from stored genetic lines might be treated as newcomers even if born centuries into the voyage. Population history can become political fuel when people are trapped inside one story for too long. The archive would need to preserve complexity, not only pride. A healthy ship might deliberately cultivate multiple forms of belonging. People could belong to families, work groups, learning cohorts, neighborhoods, maintenance traditions, research teams, artistic circles, and the vessel as a whole. No single identity should become strong enough to divide the population beyond repair. Shared rituals might mark births, apprenticeships, successful harvests, completed repairs, remembrance days, and course milestones. These would not solve all conflict, but they could give the population repeated experiences of being one society before it fractures into smaller loyalties. The arithmetic remains beneath all of this. Births must roughly balance deaths across time. Genetic diversity must not collapse. Skills must be renewed. Food must match mouths. Medical care must match age. The number of people must be large enough to absorb accident and small enough for the ship to support. Such arithmetic is cold only when seen from far away. Up close, it is a child entering a classroom, a farmer recovering after illness, a mechanic training a successor, a couple waiting for birth approval, an elder recording a repair that no one else remembers. How long could a generation ship survive with such a population? The answer depends less on one chosen number than on whether the society can keep counting without forgetting what numbers mean. 1,000 people may be too few under one design and enough under another with genetic reserves and automation. 10,000 may offer resilience while demanding far greater food, space, governance, and energy. A population that is mathematically viable but socially broken may fail before a smaller, more cohesive one. Survival is not demography alone, it is demography held inside trust. Eventually, after enough births and deaths, the people aboard may stop thinking of themselves as a crew. Crew implies assignment, passenger implies temporary passage, colonist implies arrival ahead. The mid-voyage population may become something harder to name, a people whose entire known history is enclosed inside a traveling artifact, whose ancestry is counted through records, whose future depends on controlled growth, and whose freedom has to coexist with the limits of a world no larger than its hull. Once the population has become stable enough to continue, another inheritance begins to matter more sharply. A ship can preserve bodies and still lose the reason those bodies are traveling. It can protect genes and still allow memory to decay. It can keep children alive and still fail to tell them what Earth was, why the vessel left, and how knowledge should be carried when the planet that produced it has become more archive than place. Chapter 10. Memory without a planet. Memory aboard a generation ship would not be decoration, it would be infrastructure, as necessary in its own way as water tanks, seed vaults, pressure doors, radiation shelters, and oxygen sensors. A vessel can keep bodies alive for a time through machinery, but a civilization crossing centuries needs more than functioning systems. It needs to know why those systems matter, how they were built, which failures shaped their rules, what the destination once meant, and what kind of people the ship is trying to preserve. Without memory, the voyage becomes motion without inheritance. At launch, the archive would likely be enormous. It would carry scientific knowledge, engineering manuals, medical databases, agricultural records, legal documents, languages, art, music, literature, maps, histories, genetic information, planetary surveys, educational material, and perhaps private records from the first generation. The builders would want to send Earth forward in compressed form, as if a planet could be folded into storage drives, printed volumes, seed banks, tissue vaults, and recorded voices. Yet an archive is not memory simply because it exists. It has to remain readable, trusted, taught, updated, and loved enough to be opened. The Voyager Golden Record offers a small, real precedent for this impulse. In 1977, when Voyager 1 and Voyager 2 left Earth, each carried a record containing sounds, images, greetings, and music selected to represent something of human life. The record was not made for a generation ship, and it was not meant as a complete archive of civilization. Its power lies in its modesty. It shows that human beings, when sending machines beyond home, often feel the need to attach memory to motion. A generation ship would take that impulse and make it practical, because the people aboard would need the record not for strangers, but for themselves. The first generation might not fully understand how fragile digital memory can become over long time. Files can corrupt, storage media decay, formats become unreadable, hardware interfaces vanish, software depends on other software. Compression methods, encryption systems, database structures, and operating environments can become historical traps if the knowledge needed to interpret them is lost. A document preserved perfectly in a dead format is not really available. A library that requires a machine no one can repair is already becoming silent. For that reason, the ship's archive would need layers. Some knowledge would be digital, searchable, duplicated, and distributed across protected systems. Some would be printed or etched onto durable materials designed to survive power loss and software decay. Some would exist in teaching traditions, songs, diagrams, apprenticeship routines, ceremonies, and repeated public lessons. The most important knowledge would not be trusted to one medium. A generation ship that stores everything in one way has misunderstood time. Engineering memory would be among the most urgent forms. Every major system would need original design documents, later modifications, repair histories, accident reports, calibration standards, material specifications, software revisions, known weaknesses, and old debates about why one solution was chosen over another. A manual that says what to do is useful. A record that explains why the instruction exists may be more useful after 2 centuries. Descendants do not only inherit machinery, they inherit the hidden reasoning embedded in machinery. Medical memory would carry another burden. The ship would need to preserve records of hereditary conditions, radiation exposures, pregnancies, births, deaths, infections, treatments, allergies, surgical outcomes, psychological health, nutrition, and population trends. Privacy would matter because personal records are not public property simply because survival is shared. Yet too much secrecy could endanger future care. The ship would need laws that protect dignity while allowing doctors and population planners to understand patterns before they become crises. Memory can heal only if it is handled without turning people into files. Cultural memory would be more difficult to measure. What should be preserved from Earth? Which languages deserve teaching time when curriculum space is limited? Which histories are told in full, and which are simplified until they become legends? Which religions, philosophies, songs, stories, recipes, jokes, games, legal traditions, and family customs survive the pressure of enclosure? The archive may begin by trying to save everything, but daily life selects. Children remember what adults repeat. Communities preserve what they use. Over generations, neglect can erase as effectively as disaster. Earth would first be remembered as fact. It had continents, oceans, mountains, cities, forests, deserts, animals, weather, and a sky that did not belong to a ceiling. Later, Earth might become origin. Later still, it might become argument. Some would treat it as the sacred beginning of human life, worthy of loyalty across centuries. Others might regard it as the lost world whose decisions trap them in transit. Some might care more about the destination than the origin. Some might decide that the ship itself had become the only honest homeland. Memory would not remain neutral just because it was stored. Maps would change meaning in this process. To the launch generation, a map of Earth might show home countries, routes, coastlines, borders, climate zones, old conflicts, and places personally known. To shipborne descendants, the same map might look like a diagram of ancestry. Names may remain vivid even when experience is gone. A child may memorize the outline of a continent without ever touching open ground. Another may learn the location of an ancestor's city while living inside a rotating habitat where direction itself is engineered. The map survives, but its emotional geometry alters. Language would drift even under careful education. Words brought from planetary life would be pressed into shipboard use. Outside might mean beyond a sealed compartment. Weather might describe humidity cycles in crop zones. Ground might mean the inner hull. Sunrise might mean scheduled illumination. Over enough generations, pronunciation, idiom, technical slang, childhood phrases, and ritual language would shift. The archive could preserve older forms, but living speech would keep adapting to the world that mouths actually inhabit. A language cannot be kept unchanged by storage alone. That drift might frighten those responsible for the mission. If language changes too much, old manuals may become harder to understand. Legal documents may need interpretation. Historical recordings may begin to sound formal, sacred, or strange. A phrase that was once plain may require teaching. The ship would therefore need linguistic maintenance as seriously as mechanical maintenance. Translation across time would become a profession, not only between languages, but between earlier and later versions of the same one. Recorded voices could become especially powerful. A founder explaining a repair, a scientist describing the target star, a child from the launch generation singing a song learned on Earth, a doctor leaving warnings about a disease outbreak, a grandmother speaking a language no one uses daily anymore. Sound carries presence differently from text. It does not only say that someone existed, it preserves breath, accent, hesitation, age, and the small human textures that make the dead difficult to reduce to data. Yet recorded memory can also become too authoritative. A message from the founders may be treated as law long after circumstances have changed. A warning meant for one century may be misapplied in another. A speech given during departure may become a political weapon. The dead cannot answer questions about new conditions. A mature ship culture would need to honor founding memory without being governed by it absolutely. Reverence may preserve identity, but adaptation preserves life. The archive would therefore need procedures for revision. New knowledge must be added. Old errors must be marked. Outdated instructions must be retained for history, but separated from current practice. Disputed events must be recorded with enough honesty that later generations do not inherit only the winning faction's version. A ship that edits its past too freely becomes unstable in one way. A ship that refuses to revise its past becomes unstable in another. Memory has to be conserved and corrected at the same time. There may be archive rooms where children first meet Earth as a sensory record. They might hear rain through old microphones, watch waves strike rock, study animals that no longer exist aboard the vessel, listen to crowded streets, or see forests shifting under wind. The room would not be Earth, and no honest teacher could say that it was. Still, for a child who has never known open air, such records might form the first image of human origin. The danger would be turning the planet into either paradise or wound. Both are too simple for a world that was real. Scientific memory would carry a different kind of humility. The ship's people would need to preserve not only scientific conclusions, but scientific method, skepticism, measurement, revision, peer challenge, experiment, and the willingness to let evidence disturb tradition. A sealed society can become intellectually closed if it confuses inherited knowledge with final knowledge. The archive must not become a temple of finished answers. It must remain a workshop where the living can test what the dead believed. This would matter especially for the destination. The planet or system chosen before launch may have been selected from incomplete data. Later observations from the ship might refine or weaken the original case. New science aboard the vessel might reveal risks the founders could not detect. If the archive presents the destination as destiny rather than hypothesis, the ship may become unable to respond to evidence. A generation ship survives better when it remembers that its founding plan was made by intelligent people under limited knowledge. Memory would also have to preserve failure. Successful systems are celebrated easily. Failures are more often simplified, hidden, blamed, or turned into moral lessons. But technical failure requires precision. A crop loss caused by nutrient imbalance should not become a vague story about negligence. A water contamination event should not become a legend about one careless worker if the real cause was design weakness. A governance crisis should not be reduced to villains if the deeper issue was an unclear law. False memory can be as dangerous as forgetting. Public rituals may help hold complicated memory in forms people can bear. A yearly remembrance of launch, a day for the first death in transit, a ceremony for major repairs completed, a recitation of the ship's near failures, not to frighten children, but to teach that survival has always required attention. Names of those who died maintaining dangerous systems might be preserved near the compartments they protected. Ritual, when honest, can carry information through emotion without replacing the record itself. Private memory would continue beneath the official archive. Families would keep stories that never enter public history. Old recipes adjusted to ship crops. Names passed down from Earth relatives, small objects carried at launch, a ring, a stone, a printed photograph, a page from a book, a piece of cloth, a tool. These objects would not matter because of mass or utility. They would matter because a closed world needs proof that individual lives were never fully absorbed by mission logic. A civilization survives more gently when it allows people to keep small, useless things. Across centuries, some memories would still disappear. No archive can be opened equally by every generation. Some files will be neglected, some languages will lose fluent speakers, some old arguments will no longer make sense, some art will stop moving people because the context around it has faded. This loss would not always be failure. Living cultures forget as well as preserve. The danger lies in forgetting the knowledge required for survival, and in forgetting so much of Earth that the ship's people become unable to understand their own beginning. A balanced culture might eventually teach Earth in three ways. Earth as physical planet, with its gravity, atmosphere, oceans, biosphere, and star. Earth as human history, filled with achievement, cruelty, migration, invention, extinction, tenderness, error, and repair. Earth as departure point, the place whose conditions made the ship necessary or possible, depending on the story the founders left behind. None of these alone would be enough. Together they might keep memory from becoming either worship or resentment. The ship's own history would grow beside Earth's. After enough generations, launch would no longer be the only founding event. The first successful repair after Earth contact ended, the first child born beyond the outer planets, the first crop failure survived without outside help, the first major constitutional revision, the first death of the last Earth-born person, the first observation of the destination star as more than a point in the archive, all would become markers. The vessel would stop borrowing all its meaning from the planet behind it. It would begin producing memory of its own. This is the strange transformation memory would undergo in deep space. At first, it preserves what was left behind. Then it preserves what nearly failed. Then it preserves what has changed. The archive begins as a bridge to Earth, but slowly becomes the nervous system of the ship's own civilization. Its purpose is not to freeze the past. Its purpose is to let the living continue without being severed from the reasons they are alive. So a generation ship could survive machinery, hunger, radiation, and population pressure, yet still weaken if memory becomes brittle or false. It must teach children what no one living has seen. It must revise records without erasing shame. It must protect technical knowledge from myth and human history from simplification. It must allow descendants to belong to the ship without losing the thread that ties them to a planet now unreachable in practice. Memory, aboard such a vessel, is not looking backward. It is one of the ways the future keeps its bearings. Beyond memory waits motion itself. A civilization may preserve its air, water, crops, machines, people, and archives, but its length of survival still depends on the speed and patience of the voyage. Engines decide whether the crossing lasts generations or ages, and every propulsion choice changes the burden placed on the living world it carries. Chapter 11. Engines for a Century of Patience. Engines decide how much time the living world inside the ship must endure. A faster vessel asks more from energy, shielding, navigation, deceleration, and structural strength. A slower vessel asks more from society, ecology, memory, medicine, population planning, and the patience of materials. A generation ship is therefore never only a propulsion problem, but propulsion sets the size of every other problem. The engine room, whether active for years or only during great planned intervals, determines how many generations must be born before the destination changes from calculation to arrival. Chemical rockets made the first human journeys beyond Earth possible, but they are poor servants for the distances between stars. They spend propellant quickly and reach speeds that are impressive near planets but small beside interstellar distance. A spacecraft moving at tens of kilometers per second may cross the solar system with dignity, yet the nearest stars remain years of light away. At that scale, ordinary speed becomes almost stillness. The mathematics is not hostile. It is only large, and it asks whether a civilization can carry life long enough for small fractions of light speed to matter. Project Orion, studied seriously in the mid-20th century, approached the problem through nuclear pulse propulsion. Its core idea was physically bold. A massive craft could be pushed by repeated nuclear explosions behind a pusher plate, using controlled bursts of force to accelerate a vehicle far heavier than chemical rockets could manage efficiently. The proposal belonged to a period when nuclear engineering and space ambition had not yet separated into the forms later politics would prefer. For a generation ship, Orion-like thinking matters because it shows how interstellar travel pushes propulsion toward energies that feel less like ordinary transportation and more like industrial civilization concentrated into motion. Yet Orion also shows why propulsion cannot be separated from society. Nuclear pulse systems raise questions of fallout near Earth, treaty limits, launch safety, engineering reliability, shock absorption, and the willingness of a civilization to build a vessel whose departure method is itself politically and environmentally difficult. A generation ship could perhaps be assembled far from Earth, using extraterrestrial material and avoiding atmospheric launch, but that only moves the burden into a larger infrastructure. Before the ship begins its voyage, another civilization must already exist in space, strongly enough to build it. Project Daedalus, designed by the British Interplanetary Society in the 1970s, offered a different kind of seriousness. It imagined an uncrewed fusion probe sent toward Barnard's star, using pellets of deuterium and helium-3 in a staged design. Daedalus was not built, and it was not intended to carry human beings, but it demonstrated what disciplined interstellar speculation can look like when engineers force the dream into mass, fuel, staging, acceleration, and mission duration. Its importance for a generation ship lies partly in what it omits. A probe may need instruments, guidance, communication, and protection. A living vessel must add farms, clinics, schools, law, sleep, childbirth, and grief. Fusion propulsion remains one of the most tempting possibilities because fusion offers high energy density compared with chemical reactions. Stars shine through fusion, though no ship can borrow stellar ease. Human fusion systems require confinement, fuel handling, energy capture, heat rejection, materials able to survive intense conditions, and control over a process that remains extremely difficult even in stationary facilities. A generation ship using fusion would need more than a working engine at launch. It would need an engine architecture that can be maintained, inspected, repaired, and trusted by descendants who may never see it used at full power except through old records and rare burns. The sound of such propulsion, if sound carried through the ship's structure rather than space itself, would not need to be dramatic. It might enter the habitat as a disciplined vibration, a low presence transmitted through frames, tanks, and bearings during scheduled acceleration. Floors might carry a faint change in pressure. Tools might rest differently against their straps. Children might learn that certain days belong to engine watch, not because the stars outside looked different, but because the vessel's body had taken on a deeper mechanical attention. Motion across interstellar distance would be felt first as management. Acceleration is gentle only when time allows it. A ship that accelerates slowly over months or years can reach meaningful speeds without crushing its inhabitants. But long acceleration affects structure, rotation systems, fuel use, navigation, and internal life. If the habitat spins for artificial gravity while the ship accelerates along another axis, design becomes more complicated. If acceleration itself provides gravity, then the ship must maintain thrust for long periods, demanding enormous energy and fuel. Each solution moved difficulty from one part of the vessel into another. Propulsion is a bargain that travels through architecture. Robert Forward's work on light sails opened another path. Instead of carrying all propellant aboard, a craft might use an enormous sail pushed by light or microwave beams from a powerful external source. This idea changes the mass problem by leaving much of the energy infrastructure behind, perhaps near the solar system. For small probes, modern descendants of sail thinking appear in concepts such as breakthrough starshot, where tiny craft might be pushed to significant fractions of light speed. For a generation ship, the scale becomes much harder. A living vessel is not a gram-scale wafer. It is a protected world with mass enough to resist easy acceleration. A beamed sail generation ship would also remain dependent on an enormous system it leaves behind. The beam must stay aimed across vast distance. The sail must remain stable. Acceleration must not tear the structure apart. Communication between ship and beam infrastructure becomes delayed. If the home system fails, changes politics, or loses interest, the vessel may have little recourse after departure. Such a design carries a quiet social assumption. The civilization that launches the ship must remain capable and committed long after the ship has begun to move beyond reach. Antimatter appears in many interstellar discussions because matter-antimatter annihilation releases energy with extreme efficiency. In practice, antimatter is extraordinarily difficult to produce, store, handle, and use safely in large quantities. A generation ship cannot rely on a word that sounds powerful if the supporting industry does not exist. Even if future civilizations learn to create and store antimatter at scale, the containment systems would become among the most critical and dangerous parts of the vessel. The energy promise is large. The maintenance burden may be larger than the romance surrounding it. Every engine choice must include deceleration. It is easy to imagine a vessel departing. It is harder to remember that arrival at another star requires shedding speed. A probe can fly past a target and still return data. A generation ship cannot treat a centuries-long journey as a high-speed glimpse. It must slow enough to enter orbit, approach resources, or begin settlement operations. That slowing may require carrying fuel for the second half of the journey, using magnetic sails against the interstellar medium or stellar wind, relying on beamed systems near the destination, or planning complex maneuvers around the target star. Arrival is propulsion in reverse, and it may be more unforgiving because no home system waits nearby to correct failure. This is where speed becomes morally complicated. A ship moving at a higher fraction of light speed reduces the number of generations that must live and die in transit. It may spare descendants the burden of a 1,000-year crossing, yet higher speed increases the hazard of dust impacts, radiation from interstellar particles, navigation precision, and deceleration energy. A slower ship may be safer in motion and easier to shield, but it asks the living world inside to remain stable across more berths, more repairs, more opportunities for drift and failure. Neither speed nor slowness is kind by itself. The first generation might celebrate acceleration because it feels like progress. Course numbers improve, distance from Earth increases. The destination star becomes less impossibly remote in mission projections. Later generations may experience speed differently. If engines are mostly silent during cruise, propulsion becomes history rather than sensation. The great machines may sit behind sealed access layers, visited by specialists, taught through diagrams, monitored through slow-changing numbers. A child may know that the ship is moving at a fraction of light speed and still experience daily life as stillness under scheduled lamps. Cruise is the long middle state that propulsion creates and then abandons to other systems. After acceleration, the engines may rest, but the ship continues at velocity because nothing in deep space slows it much unless something is deliberately arranged to do so. This is one of the quiet gifts of spaceflight. Coasting requires no continuous pushing. It is also one of the burdens because the voyage continues whether the society remains emotionally prepared or not. Once committed to cruise, the ship cannot decide casually that the mission has become inconvenient. Navigation during that cruise would be more than pointing toward a star. Stars move, the target system moves, the launch system moves. The ship's own course changes through tiny errors, gravitational influences, expelled mass, and correction burns. Pulsars might be used as natural beacons, star trackers, inertial systems, long baseline observations, and internal clocks would all support orientation. The vessel would need to know not only where the destination appears, but where it will be after the ship has spent decades or centuries crossing the gap. Interstellar travel is navigation through time as much as space. Engine maintenance during cruise would be psychologically strange. A system that may not be used for many years still has to remain ready. Fuel containment must be checked. Nozzles, fields, reaction chambers, sail deployment mechanisms, magnetic systems, or pulse units must be inspected according to the chosen design. A dormant engine can become untrustworthy through neglect. The ship must therefore spend labor on machinery whose importance is mostly future. This is difficult for any society, because immediate needs always speak louder than distant ones. The great danger is that propulsion knowledge becomes ceremonial. People may repeat the story of the engines without understanding their working tolerances. They may preserve old diagrams but lose the practical ability to diagnose a fault. They may treat the propulsion compartments as sacred spaces, dangerous and revered, visited only by a narrow class. That path is tempting because engines of such scale naturally gather myth around themselves. A successful generation ship would need to keep the engine demystified enough to repair, respected enough not to neglect, and politically protected enough not to become a symbol fought over by factions. Fuel is memory in physical form. Whatever mass the vessel carries for future burns represents choices made before launch and sacrifices made by the civilization that built it. A tank of fusion fuel or stored reaction mass is not just propellant, it is the option to correct, slow, redirect, or survive. Using it too freely may shorten the future. Guarding it too rigidly may prevent necessary action. Later generations would inherit fuel reserves as both tool and temptation, and their laws would need to say who may authorize their use when the original mission plan no longer answers every condition. There is also the possibility of harvesting along the way, often imagined through concepts such as interstellar ramjets. In theory, a craft might gather hydrogen from interstellar space and use it for propulsion. In practice, the interstellar medium is thin, and the engineering problems of collecting enough material, handling drag, and sustaining useful fusion are severe. Such ideas remain valuable because they show the direction of the desire, a ship that does not have to carry all its future with it. But desire cannot thicken the medium between stars. The vessel must be designed according to what can actually be gathered, not what would be convenient to gather. If the ship travels slowly enough, it may survive longer than the relevance of its first destination. New observations could reveal that the target planet is less habitable than expected. The home system, if still communicating, might send updates that arrive too late to change much. The ship's own telescopes may refine the picture gradually. Propulsion then becomes tied to governance again. Can the vessel alter course? How much fuel would that cost? Does a better destination justify centuries more travel? Who decides for people not yet born? Engines create options only if the society can agree when to use them. A century of patience does not mean a century of passivity. Even during cruise, the ship would be moving through small corrections, alignment checks, fuel inspections, sail or field monitoring, radiation management, dust detection, and training cycles for engine crews who may never perform a major burn until late life. Simulations would become ritualized practice, but they must remain rigorous rather than theatrical. A failed simulation should have consequences in training. A successful one should not become complacency. The people responsible for future deceleration would have to practice an event that may define the fate of descendants. The engines would also shape social imagination. A society that believes the ship can still maneuver may think differently from one that believes it is locked into a path. Maneuverability supports political possibility. Fixed trajectory can harden destiny. If the engines are strong, factions may argue over alternate stars. If fuel is limited, the founding course becomes harder to challenge. If the propulsion system fails, the ship may become a drifting habitat whose survival question changes completely. In each case, technology alters philosophy before anyone names it as philosophy. How long could a generation ship survive then, under different engines? At one extreme, a relatively slow vessel might require many centuries or millennia, placing almost unbearable demands on ecology, population, and repair. At another, a high-speed fusion or beamed sail vessel might shorten transit to a few generations, but impose extreme energy and shielding challenges. The best answer may not be the fastest design, It may be the design whose speed, mass, repairability, shielding, and social demands remain in balance long enough for real people to live inside the compromise. The patient engine is therefore not a symbol of conquest. It is a device that transfers difficulty into time. Every meter per second gained changes how many children will be born before arrival, how many repairs must be made, how much food must be grown, how many governments must remain legitimate, how many archives must be preserved, and how long the ship must resist forgetting. Propulsion sits far from the nursery, perhaps behind locks and radiation barriers. Yet it reaches into the nursery through the number of generations that must sleep there. When the engines have done what they can, the ship still has to cross the medium ahead. Deep space is sparse, but not perfectly empty. At low speeds, its dust and particles may be minor engineering irritants. At higher speeds, even small grains and thin gas can become part of the ship's hazard landscape. The next wall of survival is not a wall at all, but the almost invisible material between stars, waiting across every kilometer of the path. Chapter 12. Between stars, dust is not empty. Interstellar space is often described by what it lacks. It has no air for lungs, no open water, no soil, no weather, no road, no shore, and no ordinary surface on which a human sense of place can rest. Yet a generation ship would not move through perfect nothing. Between the stars there is gas, dust, radiation, magnetic structure, stray particles, old material from dead stars, and the faint backgrounds left by the history of the universe itself. The medium is thin beyond any earthly comparison, but thinness is not the same as absence. Across a long enough path and at a high enough speed, even sparse matter becomes part of engineering. A ship moving slowly by interstellar standards may meet this material as a low, continuous environmental condition. A faster ship meets it differently. Velocity changes the meaning of small things. A grain of dust too small to see can carry dangerous energy when the ship strikes it at a significant fraction of light speed. A hydrogen atom becomes part of a forward radiation problem if the vessel is moving fast enough. Gas that would seem almost non-existent in ordinary density can accumulate into dose, heating, erosion, and impact calculations across years of motion. The emptiness ahead begins to acquire direction. The interstellar medium is not uniform. Some regions are more rarefied, some denser, some warmer, some colder, some shaped by magnetic fields and the remnants of stellar activity. The Sun itself sits inside a local interstellar environment, moving through material that has its own history. A generation ship leaving the solar system would cross from the Sun's influence into that broader medium, where the protective habits of planetary thinking no longer apply. It would not pass through a tunnel cleared for travel. It would pass through what remained between stars after stars had formed, lived, and returned material outward. For the people inside the vessel, most of this would be invisible. They would not see atoms crossing the bow. They would not hear dust touch shielding. They would not feel the constant arrival of charged particles as weather. The forward shield, sensors, particle detectors, impact monitors, and radiation models would translate the medium into data. A quiet number on a display might represent millions of encounters too small to name individually. The ship's front would become an instrument before it became a wall. Dust is the easiest hazard to misunderstand because dust sounds harmless. On Earth, dust gathers on shelves, enters sunlight, settles in corners, and signals neglect more often than danger. Between stars, the word covers particles whose size and speed matter more than their familiarity. At interstellar velocity, a tiny grain can release enough energy on impact to damage exposed structures, vaporize material, or send secondary fragments into protective layers. The ship would need shielding designed not only against one dramatic object, but against a statistical population of small encounters spread across the crossing. A forward shield might therefore be sacrificial by design. Layers could be placed ahead of the main pressure hull so that small particles strike, break, vaporize, or disperse before the inhabited structure is threatened. Some concepts imagine thick forward masses of ice, water, graphite, metals, or layered composite materials, Others involve extended dust detectors, plasma fields, or deployable screens placed ahead of the vessel. None of these choices is effortless. A shield that protects well adds mass. A shield far ahead complicates control. A shield that erodes must be inspected, replenished, or accepted as a finite reserve. The surface facing the direction of travel would age differently from the sheltered interior. It would collect impacts, radiation damage, thermal stress, and the slow history of contact with a medium almost too thin to imagine. Microscopic pits might become maps of the route. Detectors would count grains and charged particles as the ship entered slightly different regions. Maintenance robots might inspect scars that no human eye could interpret without magnification. In the records, the outside would appear as numbers, crater patterns, warning thresholds, and replacement schedules. Gas creates another problem. The interstellar medium contains mostly hydrogen, along with helium and traces of heavier elements. At low density, it seems like nothing a vessel should fear. At high speed, however, the ship moves into that gas continuously. Particles striking the forward structure can produce radiation, heating, and material damage. Some studies of relativistic spacecraft have noted that even thin interstellar gas becomes significant when the craft approaches a notable fraction of light speed. A generation ship would probably not move as fast as the most ambitious tiny probes, but the principle remains. Speed turns the medium into a design partner. A slower generation ship might avoid some of these harsher effects, but it pays in time. A vessel traveling slowly enough to reduce dust and gas hazards may require many more generations to arrive. More generations mean more repairs, more births, more chances for ecological drift, more cultural change, more machinery aging, and more exposure to radiation. A faster vessel shortens the social and ecological burden while sharpening the forward hazard. The route through deep space is therefore not only navigational, it is a compromise among physics, biology, engineering, and inheritance. Sensors ahead of the ship would carry special importance. A telescope can see distant stars, but dust grains and small bodies along the near path demand different forms of awareness. Radar may have limits at vast distance and for small objects. Optical systems may miss what matters until little time remains. Particle detectors, impact sensors, forward scouts, and perhaps small probes traveling ahead of the main vessel could help map the immediate environment. Yet every sensor must survive the same crossing it is trying to measure. Awareness itself becomes something that needs shielding. The ship might send small sacrificial scouts ahead, not as heroic explorers, but as practical extensions of caution. These could measure dust density, magnetic conditions, radiation levels, and unexpected debris along the route. Some might be lost, some might return data before failing, some might alter course slightly to sample a region the main vessel would rather avoid. Their information would arrive with delay, and the ship's ability to respond would depend on speed, distance, and maneuvering fuel. A warning is useful only if it reaches a society still able to act on it. Navigation would have to include avoidance at several scales. Large objects between stars are rare, but rare does not mean impossible. Rogue planets, icy bodies, comet-like remnants, and debris associated with stellar systems would be more relevant near departure and arrival. Yet the ship could not assume that the path was clean simply because space is vast. Small course changes made early can prevent large risks later. Delayed correction can become expensive. A generation ship would travel inside its own prediction of the future, adjusting that prediction whenever observation allowed. The interstellar magnetic environment may also matter, especially for charged particles and any attempt to use magnetic sails or fields for braking. Magnetic fields between stars are weak by ordinary human standards, but over large distances they shape the motion of charged particles and influence the structure of plasma. A vessel with magnetic shielding or deceleration concepts would need to understand these fields as more than background science. The medium ahead might become something to push against, however lightly, if the ship's design tried to use it for slowing near the destination. Cosmic rays remain part of this landscape. They do not belong only to the outside chapters of radiation safety. They are woven through the entire crossing, Some arrive from galactic sources, some from solar events earlier in the journey, some from interactions between particles and shielding. The ship's radiation environment would therefore be a mixture of what comes from outside and what is produced when outside material meets protective mass. The vessel's walls would reduce danger and create secondary considerations at the same time. Protection is rarely pure. It is usually a managed imperfection. The cosmic microwave background would be present too, though not as a practical hazard in the ordinary sense for a slow generation ship. It is a faint radiation field filling space, a remnant from the early universe cooled by expansion. For the ship's instruments, it might serve as part of the larger physical environment, a background against which measurements are made. For the people aboard, it would likely remain a fact taught in classrooms rather than something directly felt. Still, it would remind the scientific culture of the vessel that even apparent emptiness has a temperature, a history, and a measurable condition. There is a quiet strangeness in building a civilization around hazards no one can sense directly. A storm on Earth darkens the sky, moves branches, changes pressure, and announces itself in sound. The interstellar medium does not announce itself to the human body. It arrives as detector counts, material erosion, radiation models, shield inspections, and occasional alarms. The people aboard must believe instruments that speak for a world beyond their senses. Their survival depends on trusting data without turning data into superstition. This trust would have to be taught carefully. Children might learn early that the ship's path is not empty, even if every camera view shows darkness and stars. They might study impact patterns on sample plates retrieved from outer layers. They might see magnified images of dust craters, diagrams of particle tracks, and simulations of shielding responses. The lesson would be calm but firm. Small things moving quickly can matter. The ship is not threatened only by large visible objects. It is also shaped by countless contacts too small for ordinary sight. A major dust impact event, if one occurred, could enter the ship's history with unusual force. Perhaps a forward shield layer is damaged beyond expectation. Perhaps a sensor array is lost. Perhaps a compartment must be sealed while robotic systems assess whether the pressure hull remains safe. If the event is survived, it becomes more than an accident. It becomes a revision point. Designers yet unborn would change inspection intervals, route planning assumptions, shield allocation, or scout deployment because of one grain, one angle, one measured failure in the old confidence. Over centuries, the forward face of the vessel might be replaced many times. Its old layers could be recycled if material allowed, or stored as evidence of the crossing. A fragment of shield pitted by interstellar dust might be kept in an archive, not as a trophy, but as a teaching object. Students could run their fingers over a safe inner surface while viewing magnified records of the outer damage. They would learn that the ship had a front, that motion had a cost, and that the space between stars had touched their world continuously even when no one felt it. The crew responsible for external monitoring would live with a peculiar form of patience. Most days, nothing unusual would happen. Numbers would remain within expected ranges. The shield would age according to models. Detectors would count particles in predictable bands. Then, occasionally, a pattern would shift. A dust density rise, a radiation fluctuation, a sensor anomaly, a temperature change in a forward layer. Their task would be to notice without exaggerating, respond without panic, and preserve enough suspicion that the ordinary never becomes invisible. Speculation can widen here, but it must stay under discipline. A very advanced generation ship might use active forward clearing, lasers, or particle beams to vaporize small debris before impact, magnetic structures to guide charged particles, or swarms of autonomous scouts mapping the medium ahead. It might carry repair drones able to rebuild shield surfaces from stored feedstock. It might even adjust its course through regions of lower dust density if observations and fuel reserves allowed. These possibilities do not remove the basic fact. The path is part of the machine. The route would also shape the calendar. Course correction windows, shield inspections, scout launches, detector recalibrations, radiation surveys, and forward structure replacement cycles might become part of the ship's long rhythm. People far from navigation work might still know when the vessel entered a predicted denser region or when a shielding survey had completed. The outside medium would enter public life through scheduled caution. A society survives better when it knows what its specialists are watching. There is humility in this. Human beings may build a vessel large enough to carry forests in trays, water in loops, archives in hardened vaults, and children through centuries. Yet the ship still has to answer to dust. The scale difference is almost absurd until physics makes it practical. A grain does not care that it meets a civilization. It only meets velocity and material. The vessel's greatness, if it has any, lies in respecting the small, without being ruled by fear of it. As the ship approaches another star, the medium would begin to change again. The target system would have its own heliosphere or stellar wind environment, its own dust structures, debris belts, comet reservoirs, planetary gravity fields, and radiation conditions. Arrival would not mean the end of hazard. It would mean replacing one set of sparse dangers with a denser and more complicated neighborhood. The shield that faced interstellar dust may still be needed as the vessel enters a system where there is finally more to hit. The long crossing between stars is therefore neither empty nor crowded. It is a region where scarcity itself becomes consequential. A little gas, a little dust, a little radiation, a little uncertainty, extended across immense distance, becomes enough to shape the vessel's front, its speed, its shielding, its sensors, its training, and its memory. Deep space does not have to offer obstacles in the dramatic sense. It only has to remain material. Once the ship has endured that material long enough, a different threshold begins to form inside the population. The people aboard may have crossed so much distance that Earth is no longer a living memory in any mind. The founders are gone. Their children are gone. Even the grandchildren of the last Earthborn may have become ancestral names. A society still moving through space must then decide what it is when its origin has become a record and its destination has not yet become a home. Chapter 13. The first generation that no longer remembers Earth. The first generation that no longer remembers Earth would not arrive suddenly. It would appear through absence, through the quiet passing of the last person whose earliest memories belong to a planet. For many years before that, Earth would have already been unreachable in practice, delayed in communication, reduced in daily authority, and preserved mostly through archive. Yet living memory has a different weight from recorded memory. A person who has felt rain, smelled open soil, heard insects beyond a wall, or watched weather gather without machinery carries a form of knowledge no recording fully replaces. When the last Earthborn person dies, the ship does not change its course. Air still moves through ducts, water still returns through processes, crops still need light, children still wake beneath the scheduled brightening of their world, but something has ended in the population. No living body now contains Earth as experience. The planet remains in images, maps, genetic ancestry, legal foundations, educational records and stories repeated at meals or ceremonies. It is no longer remembered from within. This threshold may be most difficult for the generation just after it. They would have known the last witnesses. They may have sat beside them, asked questions, heard old accents, watched hands describe things no child aboard the ship had ever seen. Those elders might have spoken of wind as if it were a personality, of rain as if water could arrive without permission, of walking until the body tired without ever reaching a wall. After their deaths, the listeners would become guardians of second-hand memory. They had not known Earth, but they had known people who did. Later descendants would stand farther away. For them, Earth might be less grief than origin. Its seas and continents might feel like the ancient environment from which the species emerged, important but not intimate. Schoolchildren could memorize old coastlines without imagining them as places someone once missed with physical pain. A forest might be a biological system in the archive. A city might be a historical structure. A thunderstorm might be a recorded atmospheric event, beautiful or frightening depending on the lesson, but not a thing anyone expects to interrupt dinner. Language would show the change early. Words tied to planetary life would remain, but their meanings would bend toward shipboard reality. Outside might mean a maintenance exterior beyond pressure, not a meadow beyond a door. Weather might refer to controlled humidity in crop decks, heat management cycles, or the failure of climate regulation in one compartment. Ground might mean the inner curve of a rotating habitat. Sunrise might be a scheduled lamp transition. A child who says morning may not be wrong, even if no star has risen over a horizon. The word has followed life into another architecture. The ship's teachers would have to decide how much of the old meanings to preserve. Too little, and the population may lose the ability to understand its own records. Too much, and children may feel that their own world is linguistically counterfeit, always borrowing names from places they cannot touch. A careful education would teach both meanings together. Rain was once water falling from clouds over open ground. Rain may also be a word in a poem, a sound in an archive, a memory preserved by ancestors, and a concept in planetary science. The old word survives by being allowed to carry layers. Cultural drift would not mean decay by itself. Every human culture has changed under pressure from landscape, labor, danger, contact, scarcity, abundance, and time. A generation ship would be no different, except that its pressures would be enclosed and more visible. Songs might shorten to fit work rhythms. Old holidays might move to match ship calendars. Foods once linked to Earth seasons might be reinterpreted around harvest cycles in controlled farms. Family names might absorb occupational history. Technical slang might enter common speech until children use engineering metaphors for emotions their ancestors described through rivers, roads, or weather. The ship calendar would become one of the strongest makers of identity. At launch, years might be counted from Earth standards, linked to the orbit of a planet no one aboard would later see. Over time, the community might preserve that count for scientific continuity while adding ship-specific markers. Years since departure, years since Earth contact ended, years since the first berth in transit, years since the first major repair carried out without founder knowledge, years until predicted deceleration. A calendar does not only measure time, it tells people which events deserve to organize memory. A society that no longer remembers Earth may begin to disagree about the destination with greater freedom. The founding generation could treat arrival as the purpose that justified everything. Their children could inherit that purpose through family loyalty, but generations born far later may ask whether an ancestral choice remains binding when the people living under it did not make it, cannot verify all its assumptions, and may possess new information about the target system. Such questions would not necessarily weaken the ship. They might be evidence that the society has remained alive enough to think. Still, disagreement about the mission would be dangerous if it touched life support discipline. A faction that argues for course change, slower travel, continued ship habitation, or altered settlement plans must still help maintain air, water, food, repair, and population stability. The ship could tolerate philosophical conflict more easily than operational negligence. It would need political forms that allow descendants to revise purpose without treating survival systems as symbols to be captured. A community can debate destination. It cannot debate whether carbon dioxide should be removed from the nursery. Archives would acquire a different authority in this period. Once no one remembers Earth directly, recordings become witnesses. A video of a shoreline may be treated with reverence because no living person can correct its emotional scale. A founder's speech may become more powerful because the speaker is unreachable in every sense. Old disagreements may be flattened by curated memory. The danger is not that archives lie by existing. The danger is that living people ask them to settle questions they were never meant to settle. A mature archive culture would therefore teach interpretation. It would explain who made a record, under what conditions, for what purpose, and with what limitations. A launch message recorded to strengthen morale should not become permanent constitutional law. A technical warning written after one crisis should not be applied without context to every later system. A personal memory of Earth should not be mistaken for a complete description of the planet. The dead can guide the living, but they cannot perform the living work of judgment. The first generation without Earth memory might also become the first to feel fully native to the ship. Earlier generations may have carried some sense of loss, even if they were born aboard, because they lived among people who spoke of Earth as home. Later children may not feel that same wound. Their home has pressure doors, crop chambers, rotating floors, stored songs, water alarms, repair festivals, archive lessons, and walls whose thickness can be trusted only through maintenance. To call this lesser would be to deny the only world their bodies have known. That native feeling could bring strength. People who stop imagining the ship as temporary may invest in it more honestly. They may improve habitats, redesign schools, create art for their own corridors rather than only preserving art from Earth, compose music shaped by the rhythms of fans and work shifts, write stories whose landscapes are decks, shafts, gardens, tanks, and shielded rooms. They may cease to think of beauty as something imported from the planet behind them. A culture becomes durable when it can make beauty from its actual conditions. There is risk in that strength as well. If the ship becomes too complete in imagination, arrival may begin to seem like a threat. A planet is not only promise, it is uncertainty, weather, microbes, gravity, exposure, open distance, and an environment not designed around the habits of the transit population. People whose ancestors longed for a surface may have descendants who fear one. A generation raised inside controlled air may not instinctively trust a sky. The destination could become less like salvation and more like another unknown system demanding adaptation. The old dream of landfall might therefore divide into several meanings. For some, arrival remains fulfillment of the founding mission. For others, it is a scientific opportunity to be approached cautiously from orbit. Some may see it as a betrayal of ship identity, a demand that the only known world be abandoned for a planetary experiment. Others may hope for a dual future, with part of the population remaining aboard while others explore the surface. The ship would need to hold these possibilities before arrival forces them into choice. Social status may shift during this long middle period. In the early voyage, prestige might belong to launch veterans, original engineers, mission officers, and those with direct Earth knowledge. Later, authority may move toward maintenance lineages, archivists, life support specialists, teachers, population planners, navigators, and those who understand old systems through practice rather than memory. A person's claim to wisdom would no longer rest on having seen Earth. It would rest on keeping the ship alive, interpreting its records carefully, and preparing descendants for conditions still ahead. Religion and philosophy, if present aboard the vessel, would also change under enclosure. Some traditions might preserve earthly sacred geographies through text and ritual, while no one can visit them. Others might develop shipboard forms, linking duty, care, repair, birth, death, and the shared loops of matter into moral language. Some people may become more secular under the discipline of systems. Others may find spiritual meaning precisely in dependency made visible. A sealed world does not answer such questions for everyone. It gives every answer the same air to breathe. Death of the last earth-born person might be remembered annually, but the meaning of the ceremony would evolve. At first it could be mourning. Later it could become a marker of independence. Later still, it might be folded into a broader day of origins, where Earth, launch, first birth, first crisis, and first self-governed repair are remembered together. Rituals survive when they can carry new feeling without losing their old thread. If they cannot change, they become performances people attend without being moved. The ship's art would reveal the transformation more honestly than law. Early paintings, songs, stories, and films may recreate Earth with longing. Mid-voyage art may place Earth and ship side by side, one lost, one enclosing. Later art may treat the vessel itself as landscape, a corridor lit by agricultural spill, a sleeping compartment beside a waterline, a child floating in a training volume, an engineer's scarred hands on a panel older than any living person. These could become images of home. The ship would stop merely preserving culture and begin producing it. Science aboard the vessel would have to remain open enough to resist cultural inwardness. A society with no direct planetary experience might gradually misunderstand environments beyond its hull, even while possessing accurate records. Planetary weather, open ecosystems, geological scale, wild microbes, oceans, and uncontrolled landscapes may become abstractions. Scientists would need to keep training the population to think beyond the ship. not because the ship is false, but because arrival may require minds ready for something less managed. A closed world can make control feel natural. A planet does not owe human beings that comfort. At the same time, shipborne science would gain expertise no planet had ever developed in quite the same way. The people aboard would understand closed loops, confined ecologies, long-term repair, recycling culture, population planning, radiation geography, and life inside engineered cycles with a depth no Earth laboratory could match. Their civilization would be narrow in some experiences and rich in others. They might lose instinctive knowledge of rivers and weather, while gaining intimate knowledge of systems that planetary societies usually hide. Survival changes ignorance and wisdom together. The destination star, if close enough by then to stand out in observation, could begin to alter imagination. For early generations, it was data. For later ones, it might become an object of public attention, measured, mapped, argued over, and named in ordinary speech. Children might grow up knowing not only where the ship came from, but where it points. The star ahead could become more emotionally real at the same time Earth becomes more historical. Human belonging might stretch between archive behind and measurement ahead. Communication with Earth, if still possible, would complicate this identity. Messages from the origin world might arrive years or decades late, perhaps from a society changed beyond recognition. The ship may receive news of political shifts, scientific discoveries, climate transformations, cultural changes, or silence. A message from Earth after several generations could feel less like family correspondence and more like contact with an ancestral civilization that has continued without them. If messages stop altogether, the silence may be interpreted many ways: technical failure, distance, disaster, indifference, or simple historical divergence. A generation that no longer remembers Earth must therefore learn not to depend on emotional confirmation from behind. It can honor Earth without waiting for Earth to approve it. It can pursue arrival without needing the founders to witness its loyalty. It can revise the mission without erasing the sacrifice that launched it. This balance is difficult because inherited purposes often demand purity, while living societies require adjustment. The ship's success may depend on allowing descendants to become more than caretakers of someone else's dream. How long could such a society remain coherent? Perhaps for centuries. If its institutions stay legitimate, its archives remain usable, its education remains honest, and its material systems keep rewarding discipline. Perhaps longer, if cultural drift is treated as adaptation rather than betrayal. The danger is not that people will stop being exactly like their ancestors. They certainly will. The danger is that they may stop understanding which differences are harmless, which are necessary, and which could quietly sever them from the knowledge that keeps them alive. The first generation that no longer remembers Earth is therefore not a failure point by itself. It is a maturity test. The ship has succeeded in making human life continue long enough for origin to become history. Now the vessel must support people who belong to it without letting that belonging shrink their imagination. They must keep Earth as truth, not prison. They must keep the destination as possibility, not idle. They must keep the ship as home, not cage. Such distinctions are fragile, but so are air, water, crops, and memory. If they manage it, the voyage enters its deepest form. A human world now moves between stars with no living witness of the world that built it. The people inside are neither passengers nor founders. They are descendants, citizens, maintainers, interpreters, and ancestors of others still unborn. Their lives may never touch a planet, yet their choices determine whether anyone ever will. Ahead, the destination system waits not as a promised ending, but as another test of what survival has come to mean. Chapter 14. What survival means after arrival. Arrival would not be the clean ending that the first generation imagined. For centuries, perhaps, the destination had existed as a promise held inside numbers, a star with measured light, a planet inferred through shadow or motion, a possible atmosphere, a possible surface, a possible place where the ship's long labor might finally open into something wider. Yet possibility is not the same as welcome. A world chosen from far away may change under closer study, An atmosphere that looked promising through instruments may carry gases in the wrong proportions. A surface may be too cold, too dry, too active, too irradiated, too chemically strange, or too unstable for bodies raised inside a sealed human world. The ship would approach not as a triumphant visitor, but as a cautious, patient machine carrying a civilization that cannot afford a beautiful mistake. Its telescopes and spectrometers would study the target system with increasing precision. Its navigation teams would refine orbital paths. Its biologists would examine every hint of chemistry that might threaten crops, lungs, microbes, or human tissue. Its historians would compare new evidence with the old launch assumptions. The destination that once simplified the mission into a direction would now become complicated by detail. Deceleration would be the first gate. A vessel that has spent generations crossing interstellar distance cannot arrive usefully if it only passes the target star at enormous speed. It must slow. And slowing requires energy, fuel, sails, magnetic braking, stellar gravity assists, or some combination of methods designed long before the people using them were born. The engines that carried ancestral hope may now have to prove whether hope can become orbit. A failed deceleration could turn centuries of survival into a brief passage through the system the ship was meant to reach. If the vessel succeeds in slowing, another question begins. Orbit is not settlement. A planet below may be visible, mapped, measured, and still unreachable in practice. Landing large populations is not the same as landing probes. The ship may need smaller craft, surface habitats, radiation shelters, chemical processing systems, medical quarantine, agriculture tests, and long observation before anyone can live below safely. Generations may have crossed deep space, only to discover that arrival itself has stages, each one demanding patience from people whose ancestors already spent patience in abundance. The first surface images would carry more weight than any ordinary scientific result. Mountains, plains, clouds, ice, seas, dust, or bare rock might appear on screens in communal halls and private rooms. People who had never seen an uncontrolled horizon would study a place not shaped by human maintenance. Some might weep because the old promise had become visible. Others might feel unease because the planet did not resemble the stories built around it. A destination becomes more real when it stops being perfect. Gravity would matter immediately. If the ship had used rotation to provide an approximation of Earth-like gravity, the bodies aboard might still need adaptation to the target world's pull. A planet with lower gravity could change movement, bone loading, circulation, and long-term development. A planet with higher gravity might make every step difficult for people whose muscles and joints were shaped by ship conditions. Even a near-Earth gravity would not erase the challenge of terrain, weather, sunlight, open distance, and exposure. A surface is not merely a floor with sky above it. It is an entire system pressing on the body at once. Air would be the second gate. An atmosphere may exist and still be unbreathable. It may have too little oxygen, too much carbon dioxide, toxic compounds, reactive chemistry, fine dust, dangerous pressure, or biological uncertainty if local life exists. Even a planet considered habitable by remote observation may require sealed settlements for a long time. The descendants of the ship may have imagined arrival as release from walls, only to find themselves building new walls on a larger surface. The first outpost may resemble the vessel more than it resembles old Earth. Water would be another promise, requiring verification. Surface ice, vapor, subsurface reservoirs, or oceans might exist, but access depends on location, purity, energy cost, chemistry, and engineering. Water mixed with harmful salts or reactive compounds may need heavy processing. Ice buried beneath rock may be difficult to reach. Liquid water, if present, may carry unknown risks. A generation ship trained by centuries of recycling would not waste water simply because a planet had some. Its people would approach abundance cautiously, because their entire culture had been shaped by the knowledge that every usable drop has conditions attached. Food would not transfer easily either. Ship crops selected for controlled light, measured nutrients, known microbes, and stable indoor conditions may not thrive in alien soil or under a different spectrum of sunlight. Local soil, if the word even applies, might lack necessary nutrients or contain harmful chemistry. Microbes from the ship could behave unpredictably in new environments, and any native biosphere would require extreme care. Agriculture after arrival might begin under domes, tanks, trays, and sealed growth rooms, almost as it did in transit. The closed garden would not be abandoned at once. It would become the first interpreter between vessel and world. The question of native life would change everything. If the planet possesses even microbial organisms, settlement becomes ethically and biologically more complex. The ship's people would face the possibility of contaminating an independent biosphere or being harmed by unfamiliar biochemistry. If no life exists, the surface may be easier to claim but lonelier in a scientific sense. Either result would force the descendants to reconsider the story they inherited. They had not merely crossed toward a place. They had crossed toward an unknown relationship with a world that did not ask to become their answer. Politics would sharpen near arrival. For many generations, disagreement about the destination could remain theoretical. Once a planet fills the screens and the ship's instruments deliver new data, old arguments gain practical edges. Some may want immediate settlement, others may insist on decades of orbital study. Some may prefer to keep the ship as the primary home while surface teams work cautiously below. Some may argue that the planet is too risky and that the vessel should continue elsewhere if propulsion allows. The founding mission may not contain instructions adequate for all that the living now know. The ship itself would have a claim on them by then. After centuries, it would not be merely transport. It would contain graves, birth records, art, laws, repaired walls, familiar routes, childhood places, archive chambers, orchards or crop decks, old arguments, beloved rooms, and the accumulated labor of generations. To abandon it fully might feel impossible. To remain aboard forever might feel like refusing the purpose for which so many lived and died. Arrival would therefore divide loyalty between the world that carried them and the world that might receive them. A partial future may be the most likely. Some people remain aboard, maintaining the vessel as orbital habitat, archive, refuge, shipyard, and biological reserve. Others descend to surface stations. Some move between the two if health and gravity allow. Children may be born in orbit and on the planet, and after 1 or 2 generations the population may begin to diverge in habits, bodies, loyalties, and language. The generation ship could become the parent of 2 worlds, one enclosed and moving through controlled loops, the other exposed to the uncertain generosity of a starlit surface. If the planet proves unsuitable, survival changes meaning again. A failed planet does not necessarily mean a failed voyage if the ship remains alive. It may enter orbit around a star and harvest energy from it. It may mine asteroids, comets, or moons. It may build additional habitats using local material. It may become the seed of a space-based civilization rather than a planetary colony. The founders may have imagined land, but descendants may discover that long survival has made them better suited to habitats than horizons. This possibility would be difficult to accept emotionally. For centuries, arrival may have been described through images of walking under open sky, touching soil, breathing freer air, and letting children grow beyond walls. To replace that image with orbital industry, asteroid ice, sealed domes, and continued recycling might seem like betrayal. Yet the ship's deepest success may have been teaching humans how to survive without requiring a planet to do all the work. The destination may offer resources rather than home at first, and resources may be enough to extend the chain. How long, then, could the generation ship survive after arrival? If its systems are exhausted, if population trust has failed, if propulsion is damaged, if archives are corrupted, if the target system offers little usable material, then arrival may only expose how narrow its margins have become. But if the ship has kept its loops resilient, its machines repairable, its population flexible, and its culture capable of revising old promises, arrival could increase its life. A nearby star gives energy. Comets and icy bodies may offer water and volatiles. Asteroids may offer metals. A planet, even an imperfect one, may offer gravity, shielding, chemistry, and space for experiment. The first landing, if it happens, would be both smaller and greater than legend. A craft descends. Instruments read pressure, wind, radiation, temperature, and chemistry. Landing legs meet ground no human foot has touched. Dust, ice, rock, or something stranger settles around the pads. People remain inside suits or sealed cabins while doctors and engineers watch every number. There may be no grand speech. The most important sound may be a pump working properly in the landing module, keeping familiar air between human lungs and an unfamiliar world. Surface contact would carry a physical shock after generations inside the ship. A horizon does not curve upward into a ceiling. Distance opens without bulkheads. Light arrives from a star without passing through habitat schedules. Wind, if the planet has it, presses without machinery. Gravity pulls through a whole world rather than through rotation. Even silence may differ, shaped by atmosphere, terrain, and exposure. The body would need to learn which sensations are safe and which are warnings. A planet can be beautiful and dangerous in the same breath. Children born after arrival may become the first true bridge. Those born on the surface or partly raised there would not understand the ship as their ancestors did. For them, open terrain may become ordinary. Ship corridors may feel old, protected, ceremonial, or confining. They may inherit languages filled with transit words while developing new words for weather, soil, distance, and sky. Their grandparents may still think like people of the vessel. They may think like people of the new world. Human identity would continue changing, because arrival does not stop history. The old ship would age differently in orbit. Without continuous interstellar hazards, some burdens ease. With access to local material, repair may become less desperate. With a star nearby, energy may become more abundant if collectors and infrastructure work. Yet new burdens appear: orbital debris, planetary dust, political division, surface accidents, divergent communities, and the temptation to neglect the vessel now that a wider future seems possible. The ship that carried everyone through deep space could be taken for granted at the very moment it becomes most valuable as backup. Memory would be tested again. The story of the voyage may be simplified into triumph, suffering, destiny, error, or myth, depending on who tells it. The generations who died in transit deserve more than a single meaning. Some maintained air and never saw arrival. Some argued against decisions that later proved wrong. Some preserved knowledge no one thanked them for. Some were born, worked, loved, and died entirely inside a crossing chosen before their time. A truthful civilization after arrival would remember them not as stepping stones, but as complete human lives. Perhaps the deepest answer is that a generation ship survives as long as it can keep turning dependence into practice. Before launch, it depends on Earth. During transit, it depends on loops, repair, discipline, memory, law, and birth. Near arrival, it depends on judgment. After arrival, it may depend on the ability to stop treating its original mission as a fixed script and begin treating it as an inheritance that must meet reality. Survival is not the same as never changing. It is the ability to change without breaking the chain that keeps life possible. A ship could fail in its first decade if its loops were brittle. It could last a century with strong engineering and disciplined people. It might last several centuries if ecology, population, repair, and memory remained in balance. It could perhaps last 1,000 years or more if it became less like a vehicle and more like a self-renewing civilization with access to enough energy and material to rebuild itself. But beyond a certain point, the question changes. The ship no longer survives because it is still the original ship. It survives because its people have learned how to keep making a world. Late in the voyage, or after arrival, the oldest parts of the vessel may become difficult to identify. A pump replaced 3 times, a corridor widened, a farm deck rearranged, a shield layer rebuilt from local material, a law revised after crisis, a language altered by children, a song whose first words came from Earth but whose later verses were written in transit. Continuity does not require every piece to remain unchanged. It requires enough memory, enough care, and enough working matter for descendants to know what they are renewing. In that sense, the generation ship's true destination may not be a planet at all. It may be a condition, a human community capable of remaining alive beyond the world that made it. The planet ahead matters, the star ahead matters. Land, water, gravity, and open space matter. Yet the crossing itself teaches a harsher lesson. If human beings can preserve air, food, water, health, memory, law, repair, and tenderness inside a sealed vessel for centuries, then survival has already become something larger than arrival. The final image is not the first footprint or the first city under another sun. It is quieter than that. Somewhere in the ship, perhaps in orbit, perhaps still between stars, air continues to move through a duct cleaned by hands that learned from older hands. Water passes through a membrane and returns to a tank where sensors hold their patient watch. A crop room brightens on schedule and leaves open under measured light. In a sleeping compartment, a child breathes without knowing every name of the people who made that breath possible. The vessel rests inside motion or orbit, no longer young, no longer only a promise from Earth. Its walls hold pressure, its records remain legible, its old repairs are still doing their work. Beyond it, a star gives light to a system that may or may not become home, and within it, the loops continue, carrying one generation into another with the same unannounced care that has always kept the world alive. The journey is complete. Rest well.